尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Start. Okay. Good morning. It's a great pleasure to start the morning session of the fourth day of this conference. And the first speaker is Kumran Wafa from Harvard University, and he will talk about non-supersymmetric strings. Please, Kumran.
Thank you. It's a great pleasure to be in this conference, and thanks to the organizer for hosting this beautiful conference here, and I'm grateful that they invited me to give a talk here. I'm going to talk about non-supersymmetric strings. This is based on a number of works with many different collaborators and also some other people's works and so forth that I have put here on my slides for you to look at if you're interested later on. I will just quote them briefly during the talks. So non-supersymmetry at low energy is what we have in our universe, and the problem is that non-supersymmetric string vacua are not well understood. We do have examples of them, but we don't have much tools to study them. Now, we expect whenever you have this to get some kind of potentials. Typically, we don't have flat potentials. When you have no supersymmetry, there's no reason for it to be. And we know from observations in our universe that if there are such potentials, their slope is incredibly small. Now, in fact, in Planck units, motivating lambda CDM by the fact that the slope of these potentials, if they exist, is observationally so small, less than 10 to the minus 122, which naturally suggests that the slope is 0. And this is one of the motivations for lambda CDM, that if there is such potential, we are at its minimum, or metastable minimum perhaps, with slope being exactly 0. However, we should be careful. As a community, we have made that mistake once before. We already thought V was 0 because V was less than 10 to the minus 122, and we kind of tried to prove V equals to 0, and we failed. We could have declared V cannot be 0 because quantum theory does not allow it, and we should have stuck to our guns. We did not. And we later learned by observation that V is not 0. In 2018 and later 2019, we conjectured with collaborators, and in fact, I presented a talk in the Strings 2018, that perhaps it is not possible to have stable non-supersymmetric vacua. Now, this went against observations at the time because we thought that we are in a stable vacuum or metastable vacuum. Observations suggest lambda CDM works pretty well. But nevertheless, again, motivated by string theory examples, we conjectured that the slope is bigger than or equal to a multiple of V of order 1 in Planck units. Now, this statement is a very specific statement, and somehow it suggests that the slope, the scale of the slope, is set by the V itself. So it makes a prediction that if C is order 1 in Planck units, we are saying that the slope is 10 to the minus 122 plus or minus 1. This is a very specific prediction. So just saying that we have order 1, that means we have no prediction, is not true. We have a very specific prediction when you remember V is so small. Now, this was motivated by observation in string theory. It's a conjecture, still remains a conjecture. And it is, if you combine this idea with the distance or duality conjecture, which suggests that you, at extreme limits of string vacua, you always have a dual description, basically. It suggests that whenever you have light towers, and in which case, whenever you are at the extreme corner, and lambda being so small, namely 10 to the minus 122, is such an example, it suggests you must have some dual description in terms of some light towers. And in those cases, we again have a logarithmic slope condition that the slope of the dark matter mass, or the tower mass, more specifically, is order 1 number in Planck units times m. And based on these observations and the fact that lambda was small, we suggested in a paper in 2019 that maybe this tower plays the role of dark matter itself, which suggested that the dark matter slope as a function of this field is also an order 1 parameter. So we gave a 2-parameter model of extension of lambda CDM with 2 constants C and C prime order 1 in Planck units. This is certainly a very strange relation from the viewpoint of particle phenomenology. Why should the slope of dark matter mass have anything to do with the mass of dark matter? Again, in 2019, when we proposed this model based on string theory observations, there was zero evidence of it. And when we checked with cosmology data, it did no better than lambda CDM. Now, this kind of parameters are naturally realized in the dark dimension scenario with one extra micron length dimension with the KK tower playing the role of dark matter. This is kind of a natural realization of this idea, but this model is somehow more general, suggesting order 1 parameters for these slopes. What are the restrictions we have for C? Based on Transplanckian censorship conjecture, which is a conjecture, it suggests that when you go far in the field space, the slope of this logarithmic slope of the potential is bounded by 2 over square root of d minus 2, which is the bound which basically says you cannot have an inflationary expansion when value of phi is large. In 4 dimensions, this means it's bigger than or equal to square root of 2 in 4 dimensions. This statement is satisfied by all the string theory examples we know. So this statement is not controversial. We have huge amount of evidence. Every construction in string theory satisfies this bound. So the slope at infinity in all the string constructions satisfies this bound. And this can be derived from Transplanckian censorship conjecture 2, which gives you an evidence for TCC. Basically, asymptotically, it is checked in all the string theory examples. TCC also gives you a statement about C away from far away in field space, even in the interior of field space. It suggests that even if C is 0 at some place, even if the slope of potential vanishes, on the average in a given region, it's above this value, which in 4 dimension means that the value of the slope, the logarithmic slope on the average, is bigger than 0.82, again in Planck units. Now, as far as C prime, this was the slope of the dark matter mass with the field. There are bounds on long-range forces because exchange of this field phi, which is basically massless, leads to a fifth force on the dark sector. And there's an experimental bound that the fifth force, compared to gravitational force, is bounded by 0.2. And from this, we learn some bound on C prime. So now, recent observations by DESI and DES experimental groups in the past couple of years have changed the story somewhat. It suggests that the dark sector lambda CDM seems to be in some kind of a tension with observations. And we ran our model of this 2-parameter model last year with just these 2 parameters, assuming it's constant. So basically a local approximation for the slope. And we found, just by fitting with observations, C was -1 plus or minus 0.2, and C prime was 0.05 plus or minus 0.02. Now, these values are very well consistent with these. First of all, it is slightly bigger than the average value, which is reassuring, by the average value bound, which is reassuring, -1 compared to 0.82. It is not at the asymptotic limit, which should have been bigger than 1.4. C prime is 0.05, which is less than the astrophysical bound, which was the fifth force bound, which is 0.2, but not too far away from that bound, a factor of 4 in C prime. Now, so this is the plots for what we found with the MC runs. This is the CPL parameterization, which parameterizes the extension of the lambda CDM with the value of the W now and the slope, W0, WA. And this is what you get from combining the DESI observation with CMB or with CMB and some different supernovae data sets. And the significance you find here that you find by this phenomenological parameterization fit is 3, 3.7, and so on. The biggest you got is around 4.1. And when we fit our model, C and C prime, we got very similar significances. And this is the plot of C and C prime we got. Lambda CDM is over here, and as you can see, we are far from the value of the lambda CDM. So now the observations are favoring the model we had proposed in 2019 based on this idea of the Sitter conjecture, which we presented in 2018. So this is the beginning of some kind of a, I would say, a stringy prediction, not a post-diction, of observations. Now, the observations are, of course, not quite settled. In fact, even since last year, they have updated the data for the supernovae. So the supernova data set got recalibrated, and the significance went down from these results. So the significance that they had went down from these values to lower values to around 3. And so we did the same thing with the recalibrated data, and we found they also went down for us also to around 3. But actually, it made the model better, surprisingly. Because if you look at the values we had for C, you had some kind of a prediction which varied depending on which data set you used. But after you recalibrated, using the recalibrated data sets, they coincided now. So our data set, our model actually could have been, if we were bold enough, we could have said it maybe anticipates a kind of a recalibration necessary. And indeed, as you can see now, the fit is even more perfect for all the data sets. Now, you might say, well, that's to be expected. After all, the data should be consistent with each other, so whichever model you use should be more consistent. That's not necessarily the case. And in fact, if you do the CPL parameterization, and you do the same question whether the recalibration fixed their kind of problem, it doesn't quite do that. You see, the value of W0 had for different data sets was like this before recalibration, and it's like this after recalibration. Not so for our model. So our model is actually a very simple phantom-free model, motivated by string theory, which fits the data beautifully up to now with 3 sigma significance, and it's quite exciting. Perhaps it may be one of the first predictions of string theory as data rolls in. W0 is the value of W now, the W parameter, pressure over the density of dark energy, and WA is roughly the slope of it as a function of Z, the redshift. Now, so as I said, this reassuring that the value we got 1 is the kind of the range that we have, but it's less than the infinity, so we are not at infinite field range. In other words, if you look at the potential, at far away in infinity, the slope, logarithmic slope should be bigger than square root of 2. But the value that fits the data is around 1, which is not unreasonable if you have some kind of a unstable, let's say, critical de Sitter. It could, for example, be somewhere here. But how do we construct the example in string theory? So that means that we really need to go towards the center, towards the regions which is strongly coupled. We cannot stay completely in the weak coupling regime which predicts C should be bigger than square root of 2. Observation is telling us it can't be. So we should begin to understand how to deal with strong coupling phenomena in non-supersymmetric theories. Because phi itself should be viewed as some kind of a, as the duality conjecture suggests, the large value of phi is the weak coupling region, so we are back to the strong coupling regions. This is somewhat in line with the Dine-Seiberg picture that when you have such scalars, only at one corners, the weak coupling corners, can we say something using perturbation theory, but we really need to go inside. We really need to have something to say about inside if we want to have something to say about the real world. How do we do that? Well, the first question might be, can we identify points in the potentials for which it's critical? Now, we don't need it to be metastable anymore because rolling is fine. The data is fine with it. We shouldn't kill ourselves to find a metastable positive V because the data could very well prefer the positive rolling potential. So we shouldn't kill ourselves for that, but we really need to be somewhere near 0 because it's far away from it's not too close to the asymptotic values. So can we find critical points of potential which is positive and breaks supersymmetry in a reliable string theory constructions? That's the question we are posing. Well, in fact, there is an idea to do that. Namely, if you find symmetries of theory at strong coupling, if you have symmetries for which fixes the moduli point, then gradient of the potential at those points would automatically be 0. This is just because of the gate symmetry. At those points when you have extra symmetries, if it is complete, if it acts on the tangent space on these scalar field moduli completely, irreducibly, by that I mean without eigenvalue 1, then you can predict that the slope would be 0, grad V would be 0 by gauge invariance. So symmetries can lead to these points. That we can trust potentially if we can have a reliable way of understanding the existence of symmetries in non-supersymmetric theories. This strategy was used in non-geometric flux compactification, which are mirror of rigid Calabi-Yau and used by Landau-Ginzburg theories. And we found some isolated critical points in particular. These were given by n equals to 1 supersymmetric theories for which we found points by going to symmetry points where W vanished, but V was critical by the symmetry argument. And so you naturally get the unstable de Sitter point. So these in the type 2b language would correspond to going to the Landau-Ginzburg point with some flux vacua and orientifold, add strong couplings of type 2b, tau equals to I, or the third root of unity. So now we have reliable examples where we do have critical points with positive potential. In fact, other isolated de Sitter critical points were also found in other works, again, at symmetry points, partially using symmetries, but not fully using symmetries. Now, the main challenge is to identify duality groups for non-supersymmetric vacua. And so here I want to give one example where it's actually quite much easier than this other example we found, which is easy to identify symmetry points. And that's just Scherk-Schwarz compactification. Already we can identify critical points in these theories. So let me remind you about a duality we well know. Take M theory on T3, let's say 3 circles, orthogonal, and that's a dual. If you dualize, if you go to type 2a and dualize these 2 circles to 2b, one of them, this one, you get type 2b S1 times S1, and we put periodic boundary conditions for fermions. This is the usual duality groups, comes from the SL3 of M theory and SL2 of type 2b combined, gives you the duality group in this theory. What happens in the Scherk-Schwarz version of this? Well, let's take the third circle, the last circle, and make it anti-periodic. If you make this anti-periodic, the duality group by diffeomorphism will change to the subgroup of SL3 and subgroup of SL2, which preserves the structure. So namely, it will be a subgroup of SL2 which preserves 0, 0, 1 mod 2, and the subgroup of SL2 which preserves 0, 1 mod 2, which is what's called the level 2 subgroup of SL2Z. And you can actually find critical points of the potential. There's the analog of the tau equals to I for this theory. So the duality group is already strong enough to go to strong coupling point and find the critical points of this theory. So therefore, even though we don't know too much about how the potential of this varies, we know at some particular point it's critical. So in fact, you can use the same kind of idea to go even further down in dimension 8, 6, 5, and 4, for example, as we did in this recent work, to find critical points. And they, for example, correspond to the torus, where you have cubic torus with the radii fixed by self-duality conditions, and a half-diagonal shift with a -1 to the f and integral value of c. And this can be, that sounds like a very simple way to get some very non-trivial examples, well, simple examples, but easy to argue that they are critical points. And interestingly enough, they give rise to the extension of the level matching conditions, which is quadratic relation that we are familiar with in the context of string orbifolds. But the level matching condition gives you new quadratic relations, which is duality invariant kind of statements, which is slightly different from the usual level matching. For example, the conditions you get if you put M theory on T5 is that if you do the generalization of these kind of shifts, you find you get the pure spinor-like conditions arising and replacing what used to be the quadratic relation for level matching. So now let me shift gears to the, oh boy, I have only 5 minutes. So to the next topic, which is the rest half of my talk, which is type 0a and type 0b. So how about non-supersymmetric theories in 10 dimensions? So why are we even going down in dimensions? We already have non-supersymmetric theories already in 10 dimensions. We better go back and do our homework well, understand what do we know about non-supersymmetric theories already in 10 dimensions. It's about time to revisit that, maybe a bit too late already, but we should do it. So the simplest example of non-supersymmetric one is just type 2a or type 2b modded out by -1 to the space-time supersymmetry, which gives you 0a and 0b, respectively. The spectrum of these are the same as 2a and 2b, except you delete all the fermions because of the projection, and you get from the twisted sector, you double the extra Ramon-Ramon sectors, you double them, and in addition, you get a tachyon. So for example, the scalar fields in 0a are the string coupling that you used to have plus a tachyon. In 0b, it's the axiodilaton plus a complex combination of tachyon plus the new axiodilaton copy, the axion copy, I mean chi prime. So you get the complexified analog of tau. Now, the first question to ask before asking anything else, do we know anything about the global structure of these parameter space? What happens? What's the meaning of these parameters, the lambda, tau, and t and z? Do we understand the global structure of the moduli space? By moduli here, I don't mean flat potentials, but just the moduli as fields. So this is the recent proposal in this paper with Baikara and Dudas, which is using the following hint. If you look at 0a, as I said, we have double the Ramon-Ramon fields. We have two U1s, a plus and a minus. So if this has anything to do with dualities, as in M theory, you would naturally look for two circles. In fact, this theory does have these zero branes, two different kinds, plus and minus, with the masses given by 1 over lambda s. It was studies that Gabardine and Bergman and others were doing long ago, and they studied these kind of D branes, and they find these zero branes of this type for this theory. So it sounds like very similar to 2a. So this would suggest that you have two circles, one for each of these U1s, if you want to geometrize this, just like in M theory. In fact, people even studied what happens if you give VEF to tachyons, and they found that these two different masses change differently when you give the tachyons. So giving tachyons changes the mass, and if you want to geometrize it, you find that they go in opposite ways. So one of them would have to increase in size and the other one decrease. So the tachyon sounds like related to the difference in the size of the circles. So this suggests that somehow M theory on this union of these circles should be somehow related to 0a. But this cannot be, because this is a disconnected space. This cannot possibly be a consistent quantum gravity where we have only one graviton. So how can we deal with this? So it's natural to just join them. Now, this joining them is bizarre. I would say I would not have done this. First of all, it's singular space. And secondly, it naively breaks the U1 times U1 symmetry that you wanted to have in the first place. So somehow the question is there any meaning to this geometry of function space motivated by this picture? So let me assume that there is a meaning to this. So for example, if you write the metric, now you have two different circles. You naively get a mu plus and a mu minus this way. And the radii of the circles will appear there as independent fields like there. And if you put the conditions on these fields to satisfy strong smoothness property or disconnected resolution or connected resolutions, you get the right spectrum of 0a. And you moreover find that people did study what happens if you go to higher order of tachyon VEF, at least up to order 2 they went, and it was conjectured by Garuzzi that perhaps they sum up to this expression. This has not been checked beyond order 2. Up to order 2 is consistent with this. And let me assume this is correct, this expression. If you take this expression and use this, you find this map between the string coupling constant and the radii of these two circles. At least the naive picture will give you this. The tachyon will be related to the difference of the square of radii, and the lambda string squared will be corresponding to the cube of the radii in this particular form, symmetric combination. So giving VEF to the tachyon would correspond to shrinking one circle relative to the other. The fact that some fields live on one space or the other and some in joint means that you cannot automatically disconnect the spaces together. The only way to get it disconnected is to first shrink one down, which is giving VEF to the tachyon. And indeed, that could, in principle, get you back to 2a. And people had already conjectured that this should be possible from studying tachyon condensation. For example, in this paper by Minwala and collaborators, they find that if you give wave to the tachyon, you should be able to get back from 0A to 2A. And this is consistent with this picture. Similarly, if you put this on a circle and go back to 2B, you learn similar things for the type 0B. And in that case, what you find is that the analog of S1 VS1 times S1 becomes 2 tori. So you have 2 tau pluses and tau minuses. And the tachyon, the complexified tachyon, which is T plus I chi prime, plays the role of the difference of these complex structures. And the SL2Z acts on tau and Z in the usual way we expect. So now we conjecture that the 0B has an SL2Z symmetry. The gamma-2 subgroup of it had already been pointed out by Bergman and Gabardini, and we are pointing out that the full SL2Z could be arising in this particular way. This actually leads to also new predictions for 4D quantum field theories. If you put a D3 brane in the 0B theory and go to this symmetric point, which corresponds to tau plus and tau minus 1 plus I over 2, you find that you should find a conformal field theory of SUN times SUN with this matter content. So this is actually a prediction that at some very strong coupling point, you do get a RG invariant fixed point of this theory. At one loop and so on, the beta function vanishes, but that has been argued by Klebanov and Zeitlin that's not going to last order by order, but this is saying that if you go to the strong coupling point and sit right at that point, it should be conformal. It will be interesting to study this question. Extensions of these ideas lead to duality wave for non-supersymmetric strings, it turns out. So this is the talk that you hear by Matilda. The motivations of some of the earlier part of what I talked about, which is the swampland program, some of it will be discussed by a review that Timo will give later this morning. Also, the related works have appeared by Urangan collaborators and some other works that I won't have time, unfortunately, to review. Thank you very much. And sorry, one last point. I forgot to mention the most important part, that these works actually were done with 2 amazing students who are finishing, well, actually more than 2 students, but 2 of them are graduating this coming year, so I want you to keep an eye on them. Thank you.
Thank you, Kumran, for this nice talk. Any questions? Yes, please.
Yeah, hi, Kumran. So I have 2 comments on the first part of the talk. The first one is a bit more technical. So I don't think we can really talk about what kind of vacua are predicted or generic in string theory until we understand the value of the cosmological constant, which as far as I understand is not something that you're addressing. And the only plausible mechanism that I know about for the cosmological constant is the anthropic one, which treats all contributions to the cosmological constant equally. And whereas I think this dark dimension scenario selects out the KK mode contribution as special, and I don't see why any contribution to the particular contribution to the cosmological constant should be special.
Sorry, just to make sure, I'm not claiming the generic value of lambda will be very small. So the anthropic principle is not at all contradictory with what I'm talking about. So in fact, you could incorporate the anthropic principle within the framework I'm talking about.
No, but I think you're predicting a relationship between the KK scale and the value of the cosmological
The value of the value of the V itself is correlated with the KK scale. That's true for all the ADSs, for example.
Yeah, so there's but I think this relation is not justified by the mechanism. The other comment.
Sorry, just before we go to the next question.
Yeah.
You could have said the same thing about ADS. Now, the ADS, we have a huge amount of examples where as you make the lambda to be small, you get the tower of light states. We have no counterexample.
No, but those are very simple vacua.
So,
string theory has much more sophisticated vacua
not necessarily simple. You can take various different versions of ADS, that's true. So this is just saying that if you flip the sign, the same principle is true. That's not a very strong extrapolation.
No, I think it's a very strong extrapolation because the standard model has many contributions to the cosmological constant that are much bigger than this, and those contributions are not present in those ADS examples because of supersymmetry.
Part of the issue is that the effective field theory reasonings, which suggests the picture that you are proposing or you're asking, is actually not the right picture for quantum gravity. Quantum gravity tells us that the principles of effective field theory should be rethought about because of the UV-IR mixtures, and that's something that you'll hear about from Timo, and the swampland principles actually suggest that without taking into account this mixture, you'll get wrong results like the ones you're pointing out.
In view of time, one more question, and we can continue with this discussion during the break.
Which one?
Yes, yes, one. Oh gosh, this is...
Yeah, I had a question about your T3 example
Yes.
with antiperiodic boundary conditions. So you mentioned the SL3 symmetry is broken in some particular way.
Yes.
Now, and then also for the SL2 symmetry. But the SL2 symmetry involves some regions where the volume becomes very, very, very small. And in the supersymmetric case, okay, it's been shown to be true, but it's not clear why that duality, even this gamma zero version of the duality, would continue to be true. So I'm asking, what's the evidence that we have such a duality?
The point is that if you take S1 times S1 times S1, in other words, you can be in either frame. Let's do the M-theory frame, in which case you have 3 circles with an S1 antiperiodic. You predict it is a subgroup of SL3 just by diffeomorphism.
Yeah.
That's true.
I have no complaint for the SL3.
No, at the same time, that same values correspond to SL2 of type 2b. The same values. In other words, the statement that SL2z is broken to gamma 2 independently of the value of the coupling is just a diffeomorphism invariance. In other words, take type 2b, put it on a torus, let's say, put it on a torus with antiperiodic boundary conditions. That's, of course, gamma 2 symmetry. Now you say, what if, suppose you say, does it last if you change the string coupling? The answer is no, it shouldn't, because diffeomorphism invariance doesn't change that fact. So that's a gauge symmetry. So we're just using the diffeomorphism symmetry with the spinners. So it's just that fact. Of course, we don't know what are the new fields that may appear, we don't know what's the potential, but we can be sure about the diffeomorphism symmetry.
Well, in view of real time, just Andy, very short, please.
Could you just say, when you have two U1s, why wouldn't it be 2 circles, product of 2 circles instead of the sum?
Naively, disjoint union. If you don't want to change the dimension, naively is 2 disconnected circles, S1 union S1. Naively, you want to, I'm just geometrizing, I'm working backwards from the data. I'm looking, what does 0A give us? It gives us 2 U1s, it has a...
And she is from Harvard University and Garching Max Planck Institute. And she will talk about string dualities in non-supersymmetric theories.
Okay, thank you very much, Miriam, and thank you to the organizers for the chance to speak. Let's see if I can make this work. Yeah, perfect, okay. So let me start with a little bit of big picture motivation. So as I'm sure you know, most of the efforts that have been put forward to connect string theory to low energy physics and the physics of our universe has relied on supersymmetric setups and breaking supersymmetry sort of at the very last moment. Now, this is, of course, for a very good reason, but a technical one, which is that you want control over all of the quantum corrections that arise once you break supersymmetry. But ultimately, you might say that this is a bit restrictive. We've seen already a few times that there are string theories already in 10 dimensions that are just non-supersymmetric, and beyond that, there are abundant ways by which you can break supersymmetry at some intermediate scale. So, moreover, you might worry, in the context of the swampland program, whether what we think we're learning about quantum gravity through swampland conjectures may in fact more have to do with supersymmetry or supergravity. So that, combined with the fact that we live in a non-supersymmetric universe, at least at energy scales that we can probe, makes it very important to try to understand non-supersymmetric string theory. So that's the goal, and to ultimately sort of disentangle those effects that are actual quantum, that have to do with quantum gravity, from those that are just supersymmetry and supergravity. So in this context, I want to talk about strong-weak coupling dualities today. So strong-weak coupling dualities, as you know, are these insane things that relate an ultra-strongly coupled description of physics to a semi-classical Einstein gravity plus QFT moving on that background description of physics. So of course, these things are amazing because they give us a window on non-perturbative physics, since you can recast all of the strong coupling stuff where all perturbative methods break down into observables that you can compute. Moreover, it connects, all these types of dualities connect string theories between each other and to M theory, which goes along the lines of saying that all of these different low-energy effective actions are just different facets of the same underlying quantum gravity, whatever that may be. And moreover, in the context of the swampland program, these types of dualities play a very important role. In the distance conjecture, also known as duality conjecture and emergent string conjecture, these dualities are the backbone of these conjectures, so we really think of them as being crucial to string theory. Good. So let's review the kinds of strong weak coupling dualities that we have. In 10D, let's start with our favorite supersymmetric strings. What kind of dualities do we have for these? Well, as you know, we can talk about M theory on a circle and say it's type 2a. M theory on an interval is heterotic E. Then you can play the, M theory, F theory duality game. And see all of the strong weak coupling dualities of type 2b and all of the non-perturbative physics associated to that in F theory, as well as the strong weak coupling duality between heterotic O and type 1 string. So the type of question I want to ask today is, what about the 10-dimensional type 0a and type 0b theories? What about the orientifolds of these theories? What about the 7 non-supersymmetric heterotic theories there are in 10D? And there's one step higher you can go in all of this craziness, which is to ask, what about the original bosonic string theory? So before I talk about dualities for these theories, let me just tell you a little bit about them. So these, of course, are non-supersymmetric in space-time, and all of them except the bosonic string are supersymmetric on the worldsheet. And, apparently they are completely consistent. Their worldsheets are modular invariant, which of course should be the case for any string theory worthy of the name. They are anomaly-free, or at least for local anomalies, and global anomalies have been checked for a subset of them. And finally, once you put them on a circle, they're related to each other and to the supersymmetric strings via T-dualities. So these are all elements of evidence that these theories are perfectly fine string theories and should be considered on par with their supersymmetric counterparts. Now, one thing you might complain about is that they have tachyons. Not all of them, some of them have tachyons. And of course, tachyons are not problems or inconsistencies in of themselves, but they do mean that somehow you're quantizing your theory on the wrong background and there's some sort of instability towards closed string tachyon condensation towards the true vacuum, whatever that may be. So as we've seen already a few times in this conference, this is a very difficult question, but what one can do, and what I think makes sense, is to consider theories around zero VEV of the tachyon and do perturbation theory around very small values of that VEV. That is something that is limited, but that makes sense. Good. So these theories, they may be tachyonic, but they're apparently completely fine, and so you can ask the question of whether or not they have strong recoupling dualities. So then, let's come back to the point, though, I want to make is that this question is extremely hard. In strong recoupling dualities, there's always one side of the duality where you can't do any kind of computation because perturbative methods just completely break down. So even in the supersymmetric cases, what you do is match BPS observables. But here we don't have supersymmetry, so we have no BPS observables. The second part of the talk, which is on this more sort of surprising duality between the bosonic string and an orientifold of type 0b. So you remember from, your first string theory class, or the bosonic string, is the original string, a critical dimension 26 dilaton B-field metric, and tachyon. It is usually kind of just left alone and assumed to be completely disconnected from the superstring theories. But back in '97, Bergman and Gabriel made this surprising conjecture, which is that the type 0b orientifold, which has a specific number of D9 branes in the background that leads to an SO32 gauge symmetry, is dual to a bosonic string compactified on a 16 torus, so then you end up with a 10-dimensional theory, at a specific symmetry enhancement point that leads to this SO32 gauge symmetry. Okay, you should be surprised already if you don't already know about this. But before I review this duality, let me first discuss the supersymmetric analog, just to remind you of how things work. So in type 1 heterotic SO32 duality, then you have SO32 gauge groups on both sides. And then the duality map is just the simple one where you send GS, so the coupling of type 1, to inverse itself. And what happens when you start in type 1 is that you start going to strong coupling, the fundamental type 1 string becomes heavy, the solitonic D1 string becomes light, and that D1 string is what becomes the dual heterotic string. You can play, of course, the same game with the two forms, and you can play the same game with the magnetic branes. That's all I wanted to say. Now let's come back to the non-supersymmetric case, where we're really thinking that the 0B orientifold is taking the role of type 1, and the bosonic string is taking on the role of the heterotic string. So the first thing that Berman and Gabriel pointed out was that for this specific 0B orientifold, you do not have massless chiral fermions, which of course is the first thing you should check if you're trying to match this theory to some sort of bosonic theory on the other side. So that's the first thing. But I think the meat behind this duality is the following. You're starting with type 0B, so the Raman-Raman sector is doubled, and so you have two D1 strings. And it so happens that for this specific choice, of background D9 branes, there is one string, which in this notation we'll call D1+, which has exactly the right degrees of freedom to correspond to the bosonic string compactified on a 16 torus. The way this works out is that you get the 8 left and right moving bosonic coordinates from just embedding this string in 10-dimensional space, which are just open strings stretching from the brane to itself. But then from the open strings that stretch between the D1+ and the background D9s, you get 32 left-moving and 32 right-moving fermions, which are exactly the right kinds of degrees of freedom to describe the 16 extra dimensions of the bosonic string on a torus in a fermionic language. So of course this is surprising, and this would only happen for this specific orientifold with these specific background D9s, okay? It's not something that is easy to engineer. Good. So this could be the string that in the strong coupling limit becomes the bosonic string. Finally, okay, you can try to match the massless and tachyonic spectra on both sides, and you see that there's two main differences. The first are the Narayan moduli, which of course exist on the bosonic side since you have the torus, but do not exist on the 0B orientifold side. And the second thing is the extra B field, right? I told you one of the strings can correspond to the bosonic string, but there's still the other string floating around, and we don't know what to do with it. The other string and corresponding B field, of course. Good, so what we did was to try to provide ways in which we can fix these problems and make the duality work. So let me turn to these two issues then. The first are the Narayan moduli. Now, these we're not too worried about. They're scalars, their masses are not protected. Of course, the potential itself is not a constant over moduli space. It is extremized at these special enhanced symmetry points, and at these points, the moduli are massless. But ultimately, you would expect string loop corrections to give masses to these things. It's just unprotected, or in other words, it has to happen for this duality to work. So that is not the main problem. The harder thing to deal with is this extra B field and corresponding string. So we have this other D1 minus, if you will, and the corresponding B minus field, and they're massless on the 0B orientifold side, so you want to find sort of a reasonable way in which you could get rid of these things if this duality were to work. Good, so what do we look at then? We look at the tensions of these two D1 strings. So this is the usual story. You have your string scale squared, okay, divided by the string coupling, and then you have a tachyon dependence, okay? There's a tachyon in closed string sector of this theory, and the open strings couple to it. Now, as Cameron mentioned, this closed form was conjectured by Garussi, but really you should only take it seriously for small values of T0. For that, you can just do the computation, and then he conjectured that this captures the whole thing. Good. So the first thing you can say is that, okay, if I wanted one of these strings to become the heterotic string, but the other one to just disappear from the spectrum, I cannot just take lambda 0 to inverse itself, because both of these strings have exactly the same dependence on lambda 0, and so they would have exactly the same fate. So it must be, if this duality works, that the duality map is more complicated. And it is tempting to say that it could perhaps depend on the tachyon, since the tachyon enters in the effective tension of these strings. In fact, it's even tempting to write some sort of effective coupling like this. And then you would really have a map which matches the type of thing that you end up with in the supersymmetric cases. But okay, let's try to be a little bit more precise and measure the tension of the string that we're trying to get rid of in units of the tension of the string that becomes a bosonic string. So to say in units in the bosonic string scale. And now you see that everything just depends on the tachyon. You lose the dilaton, which you could have read off from the previous slide. And so if according to Gurusi, this tachyon, the boundary of this tachyon's moduli space is 2, then you see that as it rolls down its potential, you would obtain a D1 minus, so this string that we're trying to get rid of, it would become tensionless. And so that's just something that you get from this. And it could make sense, because a D1 minus condensate could lead to the Higgsing of the corresponding B field. This type of thing already happens in supersymmetric cases. For instance, if you have an M5 that is parallel to an M9 and an M2 stretching between the two, then you have this scalar, thank you, you have this scalar phi, which parameterizes the distance between the M5 and the M9. And the scalar also parameterizes the tension of the induced string that you have on the M5 due to the M2 intersecting it. And so as you make phi small, the string becomes lighter and lighter and lighter until it hits the Hojava-Witten wall, becomes tensionless, and you leave the tensor branch, enter the Higgs branch. So the B field is Higgsed. Of course, then a whole other branch of moduli space opens with this sigma, which parameterizes the size of the instanton on the heterotic side. So what if, what if something similar could happen here, where instead of these scalars, you have tachyons playing the role, where as the 0B tachyon condenses, you end up in a whole new branch of moduli space where the bosonic string tachyon plays the role of sigma. Okay, so that's one way that this duality could work out. And there's a couple other things that we did in order to provide further evidence for these things. We looked at the 32,32 tachyon that exists on both sides of the duality and argued that the condensation of this open string tachyon would lead to the disappearance of the SO32 gauge group on both sides and generates a negative cosmological constant, at least at tree level. And then these people looked at the K-theory charged particles in the 0B orientifold. And so playing in an analogous way to what you can do in heterotic SO32 in type 1, they argued that these K-theory charged particles can be mapped to massive states in the lattice, which transform in spinor reps of SO32 cross SO32. And there was also very recently a paper that looked into more detail at these things. So please take a look. Good, so if I want you to take away anything from this talk, is the following. Of course, we didn't answer anything in like a yes or no way, because, as I said, it's a very difficult question, and there's very few things that you can try to compute. However, I do think, through all of the things I said, we did find some evidence that these dualities may very well exist, even for these non-supersymmetric strings. We understood why SO16 has these interesting features of having a fermion that sees both gauge groups and having a potential that blows up in the strong coupling limit. Moreover, we saw that tachyons are maybe not something that you just want to get rid of, and they might be important in this whole story. You can geometrize them in the M-theoretic construction, or they could play a role in the duality map itself when you talk about 0B orientifold and bosonic string. And of course, the idea that the bosonic string could be connected to all of the superstrings is very exciting and worth exploring. Good. So there's, of course, still a lot to be done. Explaining the gauge groups and the matter contents in the heterotic case, and please check out this paper again. In 9D, there's a lot of conjectures, strong weak coupling dualities that were proposed in 9D, and it would be nice to connect with them. So you go from 10-dimensional Lorentz symmetry to 9D Lorentz symmetry, which we haven't looked at yet. Then connecting to other cases where, we just did this sort of naive, give a small vev to the tachyon thing, but ultimately some people have tried to understand tachyon condensation in a sort of more precise way, and it would be nice to connect with these kinds of studies. And finally, having a microscopic understanding of S1, VS1, or these other kind of quantum compactifications, if you can make sense of these things in string theory, would be great. These people have tried. And yeah, of course, this is just the beginning of the list of things to do. And I'll just thank you for your attention.
Thank you, Matilda, for this great talk. Any questions? There is...
Hi, thank you for the wonderful talk. I have a question about classification of these theories. So in ordinary SUSY attendee case, for example, we have Green-Schwarz mechanism to cancel anomalies and so on. So you know it's SL32 or E8 times E8 and so on. So you can classify the allowed theories. Now, these constructions open up a lot of new possibilities. So I was wondering whether there are like new criteria that you're applying, and maybe under those criteria, can you like classify all the allowed theories, and if so, what are they? Thank you.
So in the thank you. In the heterotic case, that is completely classified, and these non-SUSY heterotic string theories I mentioned, some of them have a Green-Schwarz mechanism, so they all fit within that framework. It's just usually you forget about them because they're non-supersymmetric and tachyonic. But so for the heterotic case, it's been completely classified. Then, I mean, you're in 10D, right? So of the 0A and 0B theories, which you already have, then you can play the game of figuring out what are consistent or antifolds of these things. And I don't know if there's a proof, but I would find it hard to find other, other possible options. But yeah, so I think, except, there are cases that we did not discuss, just putting these things in 90 or whatever, which would, of course, broaden the scope of things. But in 10D, I would say this is pretty much it. Yeah.
Thank you.
Thanks.
Any other questions, comments? On this note, we can thank Matilda again for the great talk. There is a coffee break now, and we'll reconvene at 11 o'clock sharp.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Good morning still. We'll continue the morning session with Timo Weigand from Daisy and Hamburg University primarily. And he'll talk about recent ideas on constraining quantum gravity and swampland.
Very much, Miriam. Good morning, everybody. Thanks for being here. And let me start with a big thank you to the organizers and to the sponsors for making this amazing event possible and for bringing the whole community together, and also for giving me the chance to review some aspects on quantum gravity constraints and the swampland. So I guess we all agree that gravity is good for surprises. In particular, if we put on our hat as field theorists, we might, for example, expect that the usual rules of Wilsonian reasoning of effective field theory should also apply to quantum gravity. Naively, we would expect, therefore, that the cutoff of quantum gravity of the effective field theory should be set by the dimensional coupling, so be given by the Planck scale. And furthermore, we would naively expect that below this cutoff, below the Planck scale, there should arise no particular restrictions on the type of particles or on their interactions, in addition to the ones of local quantum field theory, like absence of gauge or gravitational anomalies. In actuality, however, things are different. The cutoff of a quantum gravitational effective field theory can be parametrically below the Planck scale. And the particle content and also the interactions can be severely restricted by extra, genuinely gravitational types of constraints. And these surprises in gravity are one way or another related to the idea of UV-IR mixing, so to the concept that in quantum gravity, the physics at the very high energy scales might affect what's going on at low energies in the IR much more than we would be expecting based on ideas of Wilsonian decoupling. So, which then are the principles that we have to take into account in addition to quantum field theory? Which are the principles that govern the construction of effective field theories that can have a consistent UV completion in quantum gravity? This is exactly the question that is addressed in the swampland program. In other words, the task is to find quantum gravity principles that allow us to distinguish between, on the one hand, the landscape of effective field theories, which can arise as low energy effective actions, low energy effective field theories of a consistent quantum gravity in the UV, and on the other hand, to distinguish this from the so-called swampland of effective field theories, which are perfectly fine as quantum field theories, but which cannot come from a quantum gravity at high energies, a term coined originally by Kumran Waffa. And while the set of swampland theories is infinite and hence gives rise to limited predictive power, the hope would be that the landscape would be a large but finite set with possibly a little bit more improved predictive power. That would be the hope, at least. So by now there have arisen a number of such quantum gravity principles that are well motivated and that form a web of different ideas that are interconnected. In this talk today, I will not be able to go into details of all of them. Rather, I'm going to focus on two main aspects, which I think are really constitutional and important for this whole program. Namely, on the one hand, I'll be focusing on the idea of universality, universal behavior at infinity in the quantum gravity moduli space. And on the other hand, on the concept of finiteness in the interior of moduli space. But as I'm trying to show here, this is really only scratching the tip of the iceberg with many, many more ideas that would deserve being mentioned and which I will only scratch upon or maybe not even be able to mention at all. In particular, in this context, I would like to invite you to check out some of the reviews that are already existing in the literature to discuss some of these many ideas and important works that I'm not going to mention. And I'd also like to invite you to check out some of the talks at other conferences, in particular this year. For example, the sister conference to the Strings Conference, the String Phenomenology Conference 2026, contains a good overview of a lot of the corpus of work that has been done here. And furthermore, in the slides, I'm going to include a few slides which I'm deliberately not showing for reasons of time, but if you would like to look at the slides later, you can use them also as references and maybe as a starting point to read on also on the topics that I'm not going to mention. Okay, so before we come to these quantum gravity principles as such, I think it's important to say a few words on the methods and the methodology that is used in this program. So when we want to set up a quantum gravity principle, one uses essentially two types of arguments that are complementary to one another. First, one tries to invoke, of course, general arguments. These should be arguments independent of a concrete ultraviolet completion. For example, they could be using some gravitational input like black hole physics, ideas about entropy, and others that should be generally gravitational in the sense that they should trivialize in the limit when the Planck scale is taken to infinity. And of these so-called bottom-up arguments, another aspect is, of course, to check consistency with other known principles, maybe also check consistency with other quantum gravity principles. And these ideas are supposed to be general and are oftentimes maybe not as rigid as we would like them to be eventually, but they have very rigid, very general in scope. On the other hand, it's very important then to confront these ideas with quantitative tests wherever possible in a top-down test of these ideas. For this, of course, we need extra assumptions, particular concrete UV complete theories, for example, string theory, which can then serve as a laboratory, as a framework to quantitatively and mathematically test these ideas. And it is here that we can and have obtained mathematical precision, but of course at the price of restricting the scope. And of course, in this context, we also have to take into account the lamppost effect. Are these now statements about string theory? Are they statements about general quantum gravity? But it's as good as it gets in this context. So general scope versus precise, and both of these types of methods are complementary and work with each other. And for example, whatever one learns in a very concrete setup like string theory can then be used to refine, maybe refute, maybe disprove, or lend further support towards some of these general ideas. And then finally, the third step is important to harvest the constraints, to deduce the consequences for theory as such, the consequences for particle physics and cosmology, if possible, and interestingly also consequences for mathematics. And I hope I'll have time to also mention a few of these examples. So more precisely, when it comes to deducing the consequences or harvesting these swampland principles, we see that these principles can act as constrained principles. That's the original idea, constraining or ruling out theories, low energy effective field theories, which would not be consistent with one or other of these ideas. They also can serve as discovery principles. It might be that consistency requires us to include extra states, extra objects in a theory in order to make it consistent with some of these principles. We'll see an example for that. They are drivers of computational advances. They might point to regions where we have to do extra work than, for example, in string theory, and motivate extra computations from a string theoretic point of view. We'll see this as well. They can make predictions for mathematics, which can then be proven rigorously in mathematics, and this has happened, and they have already motivated conjectures which have been proven in mathematics. And of course, these ideas ultimately serve as motivation for new ideas in particle physics and in cosmology scenarios, which then may be standing by on their own feet, but which are certainly related to these general ideas. So we will give examples for all 5 of these types of applications in this talk. So now let me start with 2 examples first, and I'd like to start with one very recent example that has already been discussed at this conference on Monday in Juan's talk, namely this quantum gravity principle of imaginary distance bounds. I can be very brief since this was already discussed in detail. It is the idea that in a quantum gravity theory with a massless real scalar, one can deform that real scalar in the imaginary direction only up to a certain value. There is an upper bound on a possible imaginary deformation that was computed to be given by this precise value. And this is, of course, potentially very far-reaching, because scalar fields in quantum gravity are not just scalar fields, they are also the dynamical couplings, because after all, the idea is that in a quantum gravity theory, at least in 3 or higher dimensions, all couplings should be dynamical and be given by the vacuum expectation values of dynamical scalar fields. So this imaginary distance bound is then also a statement about what can happen in the moduli space of couplings of a quantum gravity theory. There have been general ideas how to motivate this, general arguments, relying on gravitational input, as we said at the beginning. In this case, the existence of Euclidean gravitational wormhole solutions, which would lead to instabilities and which are related to these imaginary distance bounds, as was discussed in detail on Monday in Juan's talk. You can also try to lend further support to the idea then by general reasoning. For example, consistency checks and comparison to other principles. One of the consistency checks would be to study what happens upon circle reduction. And in this case, it was pointed out, for example, that if this imaginary distance bound is violated, you will at some stage meet a point where the KK gravitons in a circle reduction would become tachyonic, pointing out a instability and lending proof to the idea that you shouldn't do this deformation as far or farther than this bound. And another idea was to look at S1 reductions of these wormhole solutions in Einstein-Maxwell theory and then relate the resulting bound to the weak gravity conjecture, which is the principle that in a quantum gravity theory there should always exist some states whose charge to mass ratio is larger than that of an extremal black hole. Second type of tests would be top-down tests. You can confront the general idea with ideas, with principles in UV-complete theories. For example, in string theories, if you apply this bound, you will see that certain instantons will indeed lead down to a breakdown of the effective action before the bound is violated. So this would be a top-down test or top-down proof of this idea then in a very concrete type of constructions. And finally, you can harvest the constraint. You can deduce now possible consequences. And one of the insights was that the existence of these wormholes requires certain instantons in the theory whose action is bounded in a particular way. Bounds of this type are known as the axionic weak gravity conjecture bound. However, the precise prefactor was under debate in the literature, and these ideas fix this prefactor to a particular number. These instantons are needed in order to essentially destabilize the offensive wormhole that one would get with these boundary conditions. In any event, these instantons are then interesting from a point of view of axion physics. They constrain theories with axions. Exemplifying the use of such a quantum gravity principle as a constraint principle. So you find constraints on theory because in every theory, that's the claim, there should exist some instanton whose action over the charge should be bounded by this value, and hence non-perturbative effects cannot be too small. Okay, so this is a very recent example of such reasoning of quantum gravity principles. A second example, which starts with an idea that is much older, the no global symmetry idea, and then leading to something much more recent and very powerful, the cobordism idea. The starting point is the quantum principle here, that in a quantum gravity theory in sufficiently high dimensions, there should exist no global exact symmetries. The general argument that is well known is that at least continuous global symmetries would be in tension with the statistical interpretation of black hole entropy. So here the input is gravitational physics, in this case, concretely, the entropy of black holes. You can also look for top-down checks. This idea is indeed realized in all string theory examples and string compactifications, and you can find explicit proofs via ADS-CFT, like in this beautiful work by Harlow and Oguri. So one way or another, this absence of global symmetry seems to be related to the holographic idea, either directly or via black hole entropy. And finally, you can harvest the constraint, and this led to a spectacular insight, a spectacular new idea, the so-called cobordism conjecture by McNamara and Waffa. I will not be able to give full justice to this rich set of ideas. Let me just give you a cartoon version. The cartoon version, very roughly, is that the absence of generalized or general global symmetries in a quantum gravity should lead to the idea that this quantum gravity is unique in a sense. Because if the quantum gravity were not unique, there would be something that you cannot get rid of in the theory by deforming it in a certain way, and this would mean that the quantum gravity itself would carry charge. These are, of course, only words, but it has been made much more precise, and the way how to think about this is in terms of the generalized cobordism group associated with the quantum gravity theory. And the point is then that if you compute now these cobordism groups, these generalized cobordism groups of a quantum gravity theory, which you can do whenever you have a particular background, and if it's non-trivial, then the statement is you have to modify your theory, you have to add extra objects to the theory such that the new theory has vanishing cobordism group. And this leads to the prediction of new objects, of defects in the theory, in this case specifically, for example, new non-supersymmetric 7 branes in type 2b string theory, or defects between type 2a and type 2b, which had been speculated upon before. So the point being here that in this case, the quantum gravity principle acts as a discovery principle. It tells you what you have to add to your theory, which new objects there should be in order for the theory to be consistent with the principle. And once more, this has been a very active field of research recently. Here are some of the works, and I'd like to invite you to look at the references for more details and for the more precise definition of what I tried to summarize in very simple terms. Okay, so now that we've seen in two recent examples how this general reasoning works, let me now focus on the first of the two main aspects that I want to highlight, namely this general circle of ideas, universality at infinity. What is meant by this? The general question the swampland or quantum gravity principle program wants to approach is to ask the question, which types of quantum gravity theories can be possible at all? This, of course, is a horrendous task. So the natural starting point would be, what type of theories are possible asymptotically in the moduli space, asymptotically in the coupling space, in particular at infinite distance in the moduli space where the theory naturally becomes weakly coupled. This would be naturally the first starting point to look. And the asymptotics of quantum gravity theories far out in the moduli space are constrained by an important principle put forward by Oguri-Waffa, the swampland distance conjecture, which to some extent is the starting point for many of the subsequent developments. It's the idea that if we have a quantum gravity moduli space and we go to regions at infinite distance with respect to the natural distance on the moduli space, which coincides with the kinetic term of the scalar fields, then the theory should break down in a particular way. It should break down because an infinite tower of weakly coupled gravitational states should become light exponentially fast in the distance with a rate that is typically denoted by alpha. And this is, of course, a complete disaster. The regions far out in moduli space, these are the regions where typically the theory is weakly coupled. So this is where you would normally think that you know everything about the theory and the theory is perfectly well controlled. The claim is, in a gravitational context, the opposite is the case, namely, infinitely many states become light. So the theory far out at weak coupling and at low energies is now governed by states that come from the UV, states that in the interior of moduli space would be sitting close to the Planck scale, which become light. This is an example of UV-IR mixing. The breakdown of the effective field theory as these weakly coupled gravitational states become light is made more precise in the statement that the so-called species scale associated with that theory becomes small in Planck units. The species scale is to be thought of as the quantum gravity cutoff scale, above which the gravitational theory ceases to be describable as a weakly coupled local EFT, where this could also be the case in a higher dimensional sense. So for example, if you decompactify a theory, the species scale would be the Planck scale of the higher dimensional theory. Or in a string theory, when the string theory becomes weakly coupled, the species scale would be the string scale, above which you may still have a weakly coupled description, but not a local one as an effective field theory, as a quantum field theory, but rather as a string theory. And as it turns out, this idea of the species scale is related to the number of particles that become light. More precisely, the species scale scales with the number of particles which are lighter than the species scale. So this is an intrinsic definition in this way, where d is the number of dimensions. So if now a tower of weakly coupled states becomes light, this means that the species scale becomes small, and in other words, the cutoff of the theory becomes small. And this can become parametrically small. This was the first statement I made at, I think, the first, on the third slide or so, that the cutoff of the theory can be parametrically below the Planck scale. And shockingly, this happens precisely at parametrically weak coupling, namely at infinite distance in the moduli space. The species scale has been discussed from many other points of view and given an interpretation via minimal black hole sizes or EFT couplings, for example, in these works. And I'd like to stress once more that the nature of this tower is a gravitational tower. On top of that, of course, there can also be, in these regions of moduli space, field theoretic states which may decouple from the gravitational dynamics. For example, you could have a 5-dimensional superconformal field theory with infinitely many strongly coupled particles becoming light as well. But these play no role for these discussions. These are precisely states which are decoupling, whose charge to tension ratio goes to infinity and which decouple from the gravitational dynamics. So only the weakly coupled gravitational states are the ones that are responsible for this behavior at infinity. So, if correct, then this distance conjecture would have a number of consequences. Here are just a few of them. First of all, it means what I already said, that if you go very far in the moduli space, now in the real direction, in fact, the theory, the original theory breaks down. So in particular, this is a way to constrain parametrically large field excursion, which is something of interest to cosmologists. And this is also one of the reasons why people got very interested in this idea from a cosmological or inflationary point of view. It is also related to ideas that Qumran already talked about, the de Sitter conjecture, to gravitino mass conjecture, and has versions on the CFT dual side and an ADS distance conjecture version, both of which I will come to later in the talk. But before that, I want to dwell a little bit more about what actually happens at infinity. Because the distance conjecture does not yet tell us what the theory is that we get when the effective field theory breaks down. So in other words, what is the nature of the asymptotic tower of light states? What is the precise value of the species scale, of this quantum gravity cutoff scale? How small does it become? And how fast do the states that become light vanish? So in other words, what is the value of the exponential vanishing rate of this infinite tower of states? And this is a question which is very important from the cosmological point of view when we want to ask if this conjecture of this principle, for example, constrains inflationary models. And a refinement of this idea has been put forward as the emergent string conjecture, which states that the nature of these towers that can appear is very simple. Namely, the towers can either lead to a decompactification or can lead to a weakly coupled string theory, even if the theory in the bulk of the moduli space may have neither of these two properties. So in other words, the claim is that the moduli space at infinity exhibits universal behavior in a gravitational theory. Either a dimension grows large or a fundamental string becomes light and weakly coupled. So in other words, the claim is that the weakly coupled gravitational towers that can occur at infinite distance in the moduli space are one of two kinds. They can either, at the level of the leading tower, be Kaluza-Klein modes, or have an interpretation of the Kaluza-Klein modes upon use of duality. This is a very important qualifier. So these are, by definition, towers for which the mass is related to the original, say the lowest lying mass in this way. So there are levels, mass levels n, and the mass is related to the general tower level here in this linear way. This is how you would determine a Kaluza-Klein tower from another tower at a collider. And the degeneracy at level n is polynomial. In this case, one or several compact dimensions would decompactify at infinity in moduli space. The second possibility would be that a fundamental string, so not just a non-critical string like an E string or other things, but really a fundamental string, type 2, a heterotic string, would become tensionless and weakly coupled. And this we would see by the lightest tower corresponding to the excitations of this string. And here, of course, the clear distincting feature is this relation between the level and the mass, which is different from the Kaluza-Klein relation. And most importantly, the degeneracy would be exponential degeneracy, so Hagedorn behavior, if we like. And in this case, the theory would become a weakly coupled string theory at infinity. In the first case, in the decompactification case, the species scale, which was defined as the scale above which the theory cannot be described as a local weakly coupled EFT, would now be the higher dimensional Planck scale. So if we say decompactify one dimension, the new cutoff scale would be the higher dimensional Planck scale, which would go to 0 with respect to the original Planck scale in the limit. And in the second case, the species scale would, of course, be the string scale, above which we now have a string, but not a local description of the theory. So if this is true, then this would give us substantial more information about the rates at which these states become light, and hence about the way how the moduli space is actually constrained. Namely, these alpha rates can now take only one of two types, essentially, for the leading tower. More precisely, in the emergent string limit, we know that whatever the moduli space looked like in the interior at distance to infinity, it should look like a string becoming light, and the modulus, which governs the tension and the coupling of this fundamental string. This is a dilaton-like scalar field, and the rate at which now the string scale goes down with respect to the Planck scale is always given in this way, with alpha, this rate being 1 over square root d minus 2, d the number of dimensions. While in a decompactification limit of n dimensions, the rate at which the kk masses go to 0 with respect to the original Planck scale scales in this way. So in particular, we see that this alpha value, this exponential rate, can never be smaller than 1 over square root d minus 2. And this is important because we cannot simply avoid this breakdown of the original effective field theory by assuming that alpha simply takes a very, very, very small value. So alpha is bounded by below as a consequence. So these are very strong claims. The distance conjecture and then the refinement, the emergent string conjecture, are very strong claims. So we need to justify these claims and see if they are true or why they would be true. These are canonically normalized. These are the canonically normalized fine row. Thank you. Let me first review some general arguments on the distance conjecture. The first arguments were based on black hole entropy in these papers, one way or another. I'm going to briefly review a slightly different version that was put forward in this paper, and which also makes use of the idea of entropy bounds in gravity. So essentially, these are very similar related ideas that the entropy of gravitational objects or gravitational solutions has a say here. So the covariant entropy bound argument is as follows. First of all, the authors state that in an effective field theory, which is weakly coupled, so below the UV cutoff, the entropy, this should be S, the entropy of this effective field theory in a volume of large L, of length L, should scale with the volume times the cutoff. On the other hand, the entropy, and this is now the gravitational input, should be bounded by the covariant entropy bound, which scales in this way, which scales with the area of the volume in units of the Planck scale. And the Planck scale and the UV cutoff scale need not be the same. So in particular, combining these two, this gives a bound on the UV cutoff scale as 1 over L in terms of the Planck scale, which is a strange bound because it would mean that if L becomes very large, the cutoff would become small. So this is exactly an example of a UV-IR mixing, the second example of UV-IR mixing that would arise if we combine this covariant entropy bound, this gravitational input, with the usual idea of having a weakly coupled theory below the cutoff, lambda UV. And now in the third step, you have to relate the length of the system to the distance in moduli space. After all, I wanted to make a statement about what happens at infinite distance in moduli space, not in physical space. And here, either one uses black holes, or in this particular context, the authors look at certain running solutions in scalar fields, certain domain wall solutions, for which they constitute this relation between the length in this direction normal to the domain wall and the distance, the geodesic distance in moduli space. Such solutions exist whenever you have some geodesic trajectory in moduli space, and this delta only depends on the number of space-time dimensions, square root d minus 2 over d minus 1. And if you combine these two, you will see that the UV cutoff goes to 0. There's a Planck scale missing here. Goes to 0 in Planck units, exponentially fast in the distance, with this c just being a function of the space-time dimensions. And this is precisely the behavior that also underlies the distance conjecture now if you relate the cutoff to the mass of the particles that you would have. So strictly speaking, you would now need another argument why taking the UV cutoff down to 0 implies a tower of particles, but the types of relations that you get point already in the right direction. This was for the distance conjecture. Now, what about the emergent string conjecture? Now, in other words, the idea of how to further constrain these towers of particles. And this has been done in two series of works, which I can only very briefly mention here, namely either using ideas, again, from black hole thermodynamics and a concept known as the species entropy, or by using input from gravitational amplitudes and, again, thermodynamic ideas. These groups of authors have argued that, indeed, the only gravitational weakly coupled towers that you can get are either KK towers, meaning towers of polynomial degeneracy, or towers with exponential degeneracy, and which therefore show a string-like behavior. This follows from these entropic considerations one way or another. So this is, of course, not a proof, in particular, that the towers of the second type are really excitations of a fundamental string. This would be absolutely amazing if one could prove this from bottom up. But at least it points towards the fact that towers with exponential degeneracy are, apart from the KK towers, the only possibility that at least are following from these entropic considerations together with black hole physics and other gravitational ideas. So these are hints that this dichotomy of behavior at infinite distance seems to be reasonable and seems to be in accord with general gravitational principles. Now, these are bottom-up ideas. Let me now also present ways how to check this more concretely and more quantitatively in a top-down manner. This means that I now have to fix my UV theory in a particular way and check if these ideas are true, at least in that setup. And indeed, there has been found overwhelming evidence for both the distance conjecture and the emergent string conjecture in the context, in the framework of string and M theory compactifications. And not just in examples, but essentially in all known classes of such compactifications that we have technical control over at the moment. And the idea is here to relate this distance conjecture to a statement about what happens in the infinite distance of the moduli space of a, say, Calabi-Yau space or special holonomy space, which serves as the compactification space, and to compare the expectations to what is known about, in general, the quantum moduli space of these compactifications. So, for example, this quantum moduli space can be the Kähler moduli space of special holonomy manifolds, or it can be the complex structure moduli space of Calabi-Yau manifolds. The general idea is that first you have to understand in what way the geometry of these internal spaces degenerates at infinite distance. This is where a lot of geometric input comes. And then you have to combine this with string theory and string dualities and identify those states which become light once you wrap solitonic objects like branes and other things on cycles that become small. So dualities and string dualities play an important role here. And it is interesting to see what is actually behind this and what actually makes things work. For example, if we look at the moduli space of complex structures on a Calabi-Yau threefold, to be precise, then we see that we need quite some machinery, quite some mathematical machinery in order to understand the asymptotic behavior of these moduli spaces on the type of physics that one finds here. In particular, one can structure the discussion in two parts. First, one has to understand the effective supergravity and what happens at the level of couplings of the effective supergravity. And then one has to understand the actual states which become light and weakly coupled. For the first, one needs methods from the field of limiting mixed hot structures, which was pioneered mathematically in these papers and then studied in great detail in the group by Grimpalt, Valenzuela, and others in the complex structure side. And there one sees that the asymptotic version of the kinetic terms in, say, n=2 compactifications is indeed precisely as predicted by the emergent string conjecture. And one also finds candidates of light states, for example, from wrapped branes. But now you have to show in the second step that the cycles actually exist as special Lagrangian cycles so that you get particles which would then furnish one of the two types of towers. And for this, you really need to know about the geometry, which you have to describe as certain geometric stable degenerations in the sense of Mumford and Deligne-Mumford. And using this input, you can indeed prove the existence of these towers. You can count the states, you can count the Donaldson-Thomas invariants underlying them, and in this way really show very explicitly that this behavior of the emergent string conjecture is indeed realized. So this is a top-down way of seeing how it works, of course of limited scope, but very precise in return. Good, now let's come to some further consequences and applications. So the first big consequence would be now to use these ideas and try to rule out theories. So I could now wonder, which supergravity theories can I rule out on the basis that the behavior of couplings at infinity would not be consistent with, for example, the emergence of a weakly coupled string or decompactification limit. And I have to skip for time reasons over the so-called taxonomy program in its full generality and instead go right away to a very concrete example. In a recent paper, it was stated, the question, suppose we have a supergravity theory, or not a supergravity, no supersymmetry assumed, a gravity theory whose moduli space is given by a locally symmetric space, so essentially a Lie group coupled, divided by some maximal compact subgroup. Then which of these gravity theories with this moduli space would be consistent with the behavior at infinity that I proposed in the slides before. And indeed, this is a purely group theoretic analysis that the authors can do, and they can classify those symmetric moduli spaces whose EFTs would be consistent with these decay rates for light states, assuming that the light states exist. And for so-called minimal theories, they can indeed show that most of the theories are in the swampland, as shown in this picture, and only a handful, or or three handfuls maybe, 28 plus 3 theories are consistent with these constraining, exponential behavior for the masses, 28 of which are known theories. This would be M theory on a T8 essentially, to 3 dimensions, and 3 further theories are not yet known, but they would satisfy these relations. But all other supergravity theories in this class can be ruled out on this basis. So this is one way how, again, one would have a constraint principle. And finally, let me point out that one can also turn tables round. Namely, suppose now I'm going to go the other way. I'm going to impose the emergent string or swampland distance conjecture, and I will rule out theories not as full, but I will rule out certain regions of moduli space in those theories. More precisely, one can see that in situations with little supersymmetry, say only 4 supercharges in 4 dimensions, the classical infinite distance regions in moduli space can be heavily quantum obstructed. One can namely see, one can come to this conclusion by confronting what one actually finds in the theory with the expectations and see that various methods that would point you towards the existence of a decompactification limit or a string limit show you that these limits simply don't exist. So in other words, by coming the other direction, we can predict the existence of quantum corrections. In those cases where you can compute the quantum corrections, the predictions are in agreement, but it gives you much more information also in cases where you cannot do those computations. And this leads to new control parameters of the theory, for example, that the ratios of volumes over complex structure moduli have to be in a certain regime in 4D n=1 compactifications. And this is what I meant by driver of advanced computations, meaning that certain obstructions in the moduli space point towards the existence of corrections, and these corrections can be very important and for applications, and it's a challenge to compute them in the future. Good. So what I reviewed so far is the behavior at infinity for asymptotically flat theory, for essentially Minkowski theories and Minkowski compactifications. The first natural question is, how, if at all, do things change in the context of ADS gravity? So if I have a quantum gravity with negative cosmological constant, is there a version of the swampland distance conjecture or the string conjecture also in this context? And this is a particularly fruitful question, because if the answer is yes, you can translate it into a statement of the dual CFT, and then study this question also on the context of the CFTs as such. And indeed, this has been proposed and is known as the CFT distance conjecture. It's the statement that for d bigger equal to 3, all conformal field theories with the gravity dual originally, but you can make the statement then as a statement about CFTs even without this assumption, at infinite distance on the conformal manifold, on the moduli space of the conformal field theory, should give rise to towers. This would be the analog of the distance conjecture. Which towers? Higher spin currents, towers of higher spin fields with exponentially vanishing anomalous dimension. So this is translating the idea of having infinitely states becoming light in ADS onto the dual CFT, the emergence of a higher spin current, infinitely many higher spin currents whose anomalous dimension vanishes at exponential rate. And let's see that this is indeed what we would naively or intuitively expect in known examples. So in 4D n=4 super Young-Mills theory, for example, the moduli space is one-dimensional, the conformal manifold is one-dimensional, parameterized by the Toft coupling. The infinite distance region would be at lambda going to 0 of vanishing Toft coupling. And of course, in this case, one finds a higher spin tower of states, which, however, is of polynomial degeneracy. So naively, you would think this points to a decompactification limit, but that's not true, of course. Rather, this polynomial tower, whose mass on the dual gravity side goes to 0, is always accompanied also by an exponential tower whose mass sits at the string scale, but this is an effect of curvature in ADS, which explains the difference to the flat space intuition. So in this sense, the string limits in ADS have this well-known, slightly different description on the ADS side, that most of the states do not become really light with respect to the ADS scale, but sit at the ADS scale. But that's just an effect of curvature. The general philosophy still holds. And now if we go away from the known example of n=4 super Young-Mills, we can now study the statement as a standalone statement, and this has led to a very fruitful way of reasoning in the conformal field, on the conformal field theory side. Some directions. One direction, that the emergence of a high spin tower leads to infinite distance in the on the conformal manifold, has already been proven by Bowman, Calderon, Infante, and both overall recoupling limits and mixed recoupling limits have been studied and are being studied from a conformal field theory point of view. So in this sense, this is an idea that is imported to the study of conformal field theories and to study the global properties of the conformal manifold of the conformal moduli space on the conformal field theory side. And interestingly, in 2 dimensions, for 2-dimensional conformal field theories, things are a little bit different, but have also already been proven, at least in one direction, by Oguri and Wang. So for 2-dimensional CFTs, what appears at infinite distance is not the tower of higher spin fields, which is there anyway, but rather a tower of primary fields whose conformal dimension goes to 0 exponentially. And as this happens, if we interpret this 2-dimensional field theory as a sigma model, then a certain number of dimensions, flat dimensions, essentially open up. So this idea of decompactification limit here indeed is realized for the target space of the 2-dimensional CFT. Okay, so that's the first type of extension to ADS, so what happens for distance conjecture in ADS space. And the second type of application of extrapolation is now a bit more bold and to ask what happens if we have not a family of, not an exact moduli space of theories, but a family of theories. A family of theories with, for example, a negative or possibly even positive, but first of all, let's stick to negative cosmological constant. For example, flux compactifications or flux solutions, 10-dimensional flux solutions. And we then look at what happens as we go in this family to those members whose cosmological constant gets smaller and smaller. And the proposal is, this is the ADS distance conjecture, that as this happens, also, as we go to the family members of smaller and smaller cosmological constant, also there appears a tower whose mass scales polynomially with the cosmological constant going to 0, with a prefactor alpha that can lie in a certain regime and should not be larger than 1/2. Indeed, for supersymmetric ADS vacua, the value 1/2 has been proposed, and this is in direct equivalence with the statement that the supersymmetric ADS vacua should not exhibit scale separation, meaning that the KK scale should lie at the ADS scale, and we should therefore not think of these as lower dimensional compactifications, but rather directly as 10-dimensional solutions, where the KK scale and the ADS scale and the Hubble scale cannot be distinguished. And both of these versions are known to hold in all 10-dimensional solutions of the type ADS times some sphere, which is part of the motivation. And it's a debate in the literature to what extent they may also hold more generally. There are some types of flux compactifications that might violate them, but there is a long discussion in the literature at the moment about the validity of these compactifications. And this is interesting ongoing research. And in this sense, this general conjecture has motivated people in the community to take a much closer look again at these types of compactifications, and a lot of progress, technical progress, has been sparked by the aim of understanding the validity of these statements. Okay, now let's come to an application that we already heard about in Krummen's talk, so it can be rather brief. Namely, if we take this ADS distance conjecture at face value and apply it in the de Sitter case to our universe, it would mean that a small cosmological constant, as observed, would naturally indicate the appearance of a tower of states becoming light at a certain rate, where the rate, I said, this alpha has to lie in a certain window, and for phenomenological reasons, this is in this case bounded by the value of 1/4. So this was the idea that Kumran already discussed, that there could be a tower of states becoming light and lying in the EV or maybe milli-EV, somewhere in between regime. And if we take this at face value and combine it with the distance and the emergent string conjecture, this would mean that this tower would have to be a Kaluza-Klein tower, because the string tower would be at this low energy scale, would of course be experimentally ruled out. So this would then point to the existence of a large dimension whose KK tower is manifested by the scaling rule, a large extra dimension called dark dimension, which would lie in the regime of about 10 microns and would be associated with a higher dimensional Planck scale or species scale at the intermediate regime of 10 to the 9 to 10 to the 10 GeV. So this is one way how a cosmological scenario can be motivated by these ideas. And the phenomenology of this idea is very interesting, has been studied in detail. In particular, the KK tower can be interpreted as dark matter, and this is a way to relate, on the one hand, the cosmological constant idea, lambda, which sets the scale, then to the dark matter idea. And there have been many more ways of, or many more investigations into the phenomenological consequences of this model. So this as, once more, an idea of that gives rise to applications in cosmology. With this, I come to the last part of my talk, finiteness. So far, I've been talking about infinity, infinity of moduli space, and infinity of the number of particles becoming light. And we tried to put some order in this infinity by this idea of universality of two types of pathological behavior at infinity. Now let's go back to the interior of moduli space, where the structure that we find is not that of infinity, but of finiteness. Finiteness in quantum gravity has various aspects. First of all, finiteness of distances in moduli spaces with finite cutoff. This is essentially what I discussed. If the cutoff stays finite and doesn't go down, the distance in moduli space that I can travel must be finite. That's the converse statement to the distance conjecture. But finiteness can also refer to the number of light particles, or more precisely, the number of particles that are below the quantum gravity cutoff. And unlike in quantum field theory, the expectation is that in a quantum gravity theory, there should be a finite number of such particles. And there are more ideas of finiteness that I'm not going to review in detail for time reasons. Finiteness of amplitudes, of course, finiteness of partition functions, and also finiteness of the number of vacua themselves, not only of the structure in one vacuum, but the number of vacua, and the compactifiability of moduli space as put forward in these papers. So in the remaining few minutes, I'd just like to highlight a few ideas about the finiteness, the finite number of light states, which also has triggered some interesting ideas, again, in mathematics. And it is as follows. In a quantum gravity theory, you may have additional objects which are forced upon you by quantum gravity principles, such as the completeness principle. For example, it could be that you have a quantum gravity theory with a two-form gauge field. This two-form gauge field can couple to a one-dimensional string, a solitonic string. In a field theory, this string would be an add-on, which you may or may not consider to be physical, and in general only consider to be some operator. But the completeness principle of quantum gravity states that this object should exist as actually a physical state with tension below the Planck scale. And demanding this object to be consistent and to be consistently coupled to the quantum gravity theory now allows you to find new constraints on the quantum gravity theory that you would not be able to find without it. And this is pretty spectacular. It works essentially by using the old idea of anomaly inflow, of saying that these, say, one-dimensional strings or other objects have to be consistent. They may have an anomaly which has to cancel the anomaly flowing in from the gravity theory. And since the anomaly flowing in tells you something about the particle spectrum, if you control the theory on the world sheet, this allows you to set tight constraints on this particle spectrum in the bulk. And the most spectacular context is maybe in the context of 6D n=1 supergravity theories. These are exciting theories. People have been studying them a lot without gravity because they give rise to these beautiful six-dimensional SCFTs. But they are even more exciting if you include, or maybe as exciting if you include gravity from the supergravity point of view. These are examples of theories with two-form tensors. And they are very strongly constrained by anomaly cancellation. However, the anomaly cancellation of the bulk theory as such is not strong enough to predict a finite number of low-energy particles. On the contrary, it has been shown in these papers that local anomaly constraints alone admit infinite families with infinitely many particles, which is something that could occur in a field theory, but we would be suspicious to see this in quantum gravity. And indeed, the key idea is that since there are these two-form fields by the completeness principle, there should also be the associated strings. These strings must have a unitary worldsheet description, and with the help of anomaly inflow, you can derive certain constraints that I'm not going to go into details of, which allow you to constrain the supergravity spectrum. More precisely, in these works, in this work in particular, it has been possible to set a tight bound on the rank of the gauge group in 6 dimensions, n equal 1 supergravity, and the number of tensor fields that can occur. And I find this pretty remarkable because this is a theory with only 8 supercharges. That's the minimal amount of supersymmetry in 6 dimensions. And if we were able to do this in 4-dimensional n equal 1, we would be absolutely happy. So this is really, I think, an important result. And it shows the power of this probe-brain idea applied in the quantum gravity context. And of course, if you are now a string theorist, you can take this result and translate it into a statement about Calabi-Yau manifolds. Namely, suppose now I engineer my 6-dimensional supergravity in F-theory via an elliptic fibration, elliptically fibered Calabi-Yau threefold, then I can translate these bounds on the rank of the gauge group, the number of tensors, into bounds on the Betti numbers of elliptic Calabi-Yau threefolds. And indeed, the bounds are correctly reproduce the bounds of known examples of Calabi-Yau threefolds. But of course, we don't know all Calabi-Yau threefolds. On the contrary, we'd love to. So this gives a prediction for mathematics. And this prediction for mathematics can then be checked explicitly via geometric methods per se. And indeed, an independent mathematical proof gives a bound which currently is still a bit higher than what we get from the physics prediction, but work is underway to improve this. This is in the context with non-abelian gauge symmetries only. If you include abelian gauge symmetries, you can get similar results, and you can bound the number of abelian gauge group factors. This can be translated into model Weil groups of elliptic vibrations. You can make similar predictions, and these indeed have recently been proven with the help of mathematicians, including the case of Calabi-Yau fourfold. So this just as another example of showing how these quantum gravity ideas can also give you predictions for mathematics and inspire new mathematics. Good, let me summarize. I've tried to argue that these quantum gravity principles furnish a very fruitful arena of thinking with many interesting applications and implications. These principles can serve as constraints. For example, the axionic weak gravity conjecture constrains axions and axion physics. With the behavior at infinity, we are able to constrain supergravity theories, rule some of them out, or via probe brains, we found strong constraints on the mass spectrum. The principles can also be discovery principles. I briefly mentioned that via this beautiful cobordism conjecture, one can predict new non-supersymmetric objects in particular. They are the drivers of computational advances, for example, because they predict the appearance of quantum gravity of quantum corrections in moduli spaces, which can then be computed and partially have been computed and confirmed. They give predictions for mathematics, as I just reviewed, and they lead, and this is, of course, from a physics point of view, the most important one, to new phenomenological and cosmological scenarios, like this dark dimension, which I discussed, and which also Kumran discussed much more in his talk in the morning. So once more, this is only the tip of the iceberg. I have only focused on the universal behavior at infinity and the finiteness in the interior of moduli space. There would be much more to say. I think for the future, where the field is going is really to try to understand the deeper the actual reason behind these principles, if they are true. So to what extent is what I said a consequence or guaranteed only by supersymmetry or supergravity, as opposed to string theory, as opposed to quantum gravity as such? The explicit tests are in the context of string theory, and of course we have to be sure that we are not only, quote-unquote, making statements about string theory, but about quantum gravity. And this is why these bottom-up approaches using ideas about black holes and entropy are so important and certainly have to be developed further. And in other words, we have to go beyond the stringy lamppost, we have to go beyond supersymmetry, and most importantly, we have to understand the gravitational origin of dualities, which again, I think ties in nicely to what was said in the first two talks this morning. Thank you very much.
Thank you, Timo, for this beautiful, comprehensive talk. Any questions? Yes, there.
Yeah, thanks very much for a very beautiful talk. I wonder if you can comment on the general assumptions that you're making about quantum gravity, in the sense that the ideas you're describing are very fruitful, but they're all in a geometric context. So you have large dimensions, you're at infinite distance in moduli space and so on. But the general expectation in quantum gravity is that you don't have these things. You don't have a dimension, you don't have a space-time, you don't have parameters. So I wonder how this idea, I mean, you know, what are the basic assumptions in which you're working?
Yeah, excellent question. So I started from, or this field starts from the notion of having an effective description at low energies. This is the effective field theory from which we start. And then in this effective field theory, we incorporate really gravitational input in order to get extra constraints. So in particular, the assumption is that black holes work well at a quantum level, whatever that means, in this effective field theory. In particular, that entropy of black holes has a microscopic origin. I think many of these ideas, at the end of the day, go back to this idea. The no global symmetry idea, which then you can also relate to the absence of actual parameters, but the fact that all couplings have to be dynamical, and this, which then leads you to this moduli space. So I think this currently seems to be, which is exactly this point that I made here, that we need to understand better, seems to be one of the most important underlying ideas. And indeed, there are quantum gravity theories or proposals which do not make these assumptions and which lead to very different conclusions. For example, in asymptotic safety, the way how black holes are incorporated, if at all, is very different, and that's why these theories contradict these principles.
I see. So just let me give you an example of what. So let's say if you talk about M theory, then there is the notion that it's a theory in 11 dimension, but maybe it isn't a theory in 11 dimension.
Right. No, I didn't exactly.
Sorry. So, for example, how does the emergent string conjecture apply to M theory in general?
Very good. It would start. So it would start from some effective field theory. And then you ask, how can I, now in this module, I assume the existence of a moduli. If I don't have a moduli space, it's over. Then I can't say anything,
yes,
because it's a statement about asymptotics of moduli space. And then one of these towers, namely the deconvection tower, would then point you towards higher and higher dimensions. And now you could, for example, ask, can you go beyond 11? And in fact, this question was posed in this context. This is one of these slides which I put in just for your references. In this taxonomy picture, in this taxonomy approach, exactly that question was asked. So I combine all the constraints on the towers, which would follow from this. Can I go beyond 11 dimensions? And the answer, which they found in, say, two-dimensional moduli spaces, was no. Interestingly, they found 11 precisely to be the highest number with certain assumptions. So the idea would be to bootstrap yourself and recover that number of dimensions eventually. That would be the goal. I'm just saying that in some contexts, with some examples, with some assumptions, this has been achieved, but there's clearly room for improvement.
Thank you very much.
Okay. Okay. One more question. Yeah, another question, please.
Very good. Yeah, this would be fantastic to know. So the question was if there's a relation between the imaginary distance bound and the distance conjecture. Well, at first they look very different because the imaginary distance bound is imaginary, so it's not in the actual field space. It's a thought experiment. What would happen if I went into imaginary direction and then I get a constraint? Whereas the distance conjecture goes directly in this direction, in the real direction. I would view them at the moment as complementary. The imaginary distance conjecture is nicely consistent with the weak gravity conjecture, and the weak gravity conjecture is a consequence, that's something I could have mentioned, is a direct corollary of the emergent string conjecture. So from that point of view, they are related, but yeah, this is, should be understood better. Yeah.
Maybe you think about the Beijing function as a holomorphic function of the moduli.
Say again?
Maybe you think about the Beijing function as a holomorphic function of the moduli, and you know it had to went bad as an imaginary value that could give you a constraint about the behavior around the real.
Yeah, I think this is exactly in the way of reasoning, right? That you find an instability at certain imaginary values of your partition function of your. Yeah.
Okay, maybe one more question here.
Yeah.
Oh, sorry.
Yeah, so this is about the distance conjecture again. So if we take a say, series of Calabi-Yau connected by a conifold transition,
So,
take a series of Calabi-Yau
Yes.
connected by conifold transition.
a conifold transition,
Yeah.
yes.
And so we can keep going from one to the other through the conifold. Right? And we don't bring down infinite tower.
Exactly, because the conifold is at finite distance.
Yeah. So, but you can keep adding, right? By going from one Calabi-Yau to next Calabi-Yau.
Very nice, yes.
So does it give a bound on the number of Calabi-Yau that you can have?
Excellent question. This has been studied. So, so you're asking about the global structure of the Kähler cone. So if I go from one Kähler chamber to the other, so to speak, I do one such transition after the other. I
Yeah.
think.
So that's flop, but conifold is more general, right?
Yes,
Yeah.
yes. So for in the flop case, it has been studied, but you do not get any new results because whenever you have infinitely many, you go from one. You essentially recover the same Calabi-Yau again.
Okay, yeah.
In the flop case. For the conifold case, I'm not aware of a work in this direction, but I would think the same. I think it would not. So my intuition would be that in this way you would not actually have an infinite distance immortalized space, but that you should recover something that you saw before. But yeah.
But there is a conjecture that all Calabi-Yaus are
related,
by conifold,
exactly,
right?
yes, Reed's
So
conjecture.
unless the number of Calabi-Yaus is finite, we can go infinite distance. So in some sense, this will say.
I think it is very good. I think this points to the fact that the number of Calabi-Yaus should be finite. Which is the second one of these aspects of finiteness. I also have some slides on there if you want to look up. This Reed's fantasy indeed points towards the finiteness of vacua. And for example, there are beautiful mathematical results that, for example, the space of fibered Calabi-Yaus is finite up to certain birational equivalences, and almost all known Calabi-Yaus are either fibered or are related via a finite number of transitions to a fibered Calabi-Yau. So the evidence is pointing towards the fiberedness of Calabi-Yaus, and I think this is an outstanding question for mathematics. And I would think that your argument is another argument why the number should be finite.
Yeah, in fact, I mean, you have a more very qualitative, a quantitative formula, right? How far you can go before you bring down tower of particles. So this will probably give not just finiteness, but also the actual number, right?
The actual number, very good.
But each transition will cover a certain distance.
Mm-hmm. Yeah.
Yeah, exactly. Yeah.
Could be very long. Yeah.
You get a factor of 10 to the 5. So that's the big number, right?
Yeah.
Yeah.
Yeah. Yeah, but finite.
But I mean, you have explicit formula for the masses of the particles, light particles in terms of the distance, right? So if you have a distance of 10 to the 5 string scale,
well, I would be. Okay, I'm not sure if that distance. We would first have to compute that distance, the distance between these Calabi-Yaus. We would first have to compute that. I don't think we should. Yeah, I'm not sure what that distance is, and if this is really then. Okay, let's. I haven't done the computation. I would think that in the end, the distance should work out such that you do not find a pathology. But it would be great to challenge the conjecture by looking at it. But I would think that you have to think differently, probably about the distance between these different Calabi-Yaus. That would be my suspicion. Yeah.
Okay, on this note, maybe we should thank Tim again and continue discussion. So we are reconvening at 1:30.
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
“尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。”
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay, welcome back. We are very happy to start the afternoon session with Naomi Gendler from Harvard, who's going to tell us about the geometric axiverse.
observational bounds. So the fact that theories with large numbers of axions behave differently than those with small numbers of axions actually has consequences phenomenologically. All right, and I want to stress that, again, what did we find? Through large-scale enumeration, we discovered there are correlations between axion physics and the number of axions. And I want to stress that this is something that we would not anticipate from a model building perspective, right? These stringy axions are exhibiting novel phenomenology. And this is interesting in its own right, but what I'd like to spend the rest of the talk doing is diving in a bit to what a possible mechanism might be that drives these correlations. So is there some underlying structure that we can understand in a simple way that reproduces this behavior? Okay, so let's take a look under the hood and figure out what's actually going on here. The upshot is that in compactifications with well-controlled alpha prime expansions, so in compactifications where all the cycles are sufficiently large, we find that hierarchies in divisor volumes increase with the number of axions in the theory, or rather with H11 of the Calabi-Yau. And the fact that hierarchies in divisor volumes increase means that all the volumes get pushed up as you go higher in H11, which leads scales to come down, which has an imprint on axion physics. So the larger you go in the number of axions, the larger volume gets, which in particular pushes down axion decay constants. Okay, so what we wanted to understand was whether there's some way to understand emergent large and stringy axion phenomena from a simpler structure. And to get a handle on this, we're going to focus specifically on this statement that hierarchies in divisor volumes increase with H11. All right, so we set out to understand what distributions of divisor volumes look like in this landscape. And this is some work that I did with a graduate student at Harvard, Junyi Cheng. So what we did is for each Calabi-Yau X, we considered the following quantity. So we call these the normalized divisor volumes, and you compute them just by taking the log of the divisor volumes in a particular Calabi-Yau and dividing out by the average log divisor volume in that Calabi-Yau. Okay, and what did we find? Here I'm showing you a summary of the statistics that we found. These are just histograms of this quantity in a large ensemble of geometries with varying H11. And the first observation that we should make about these plots is that indeed there are large hierarchies in the divisor volumes. Remember that this tau hat is like log of the actual divisor volumes. So you can see here that the divisor volumes span several orders of magnitude. There's another interesting feature about these distributions, which I'll just point out, which is the emergence of this second peak at large H11. We understand completely why this second peak is there, and it's actually a really fun story at the level of the polytope, so feel free to ask me about it afterwards, but I won't get into it here. But what we wanted to do is actually ignore any kind of fine-grained structure and just see if we can approximate every distribution with one function in a way that can actually reproduce the stringy axion physics that we see at large H11. Okay, so we have this collection of distributions, and we said, let's just ignore all the finer structure of these distributions and try to approximate it with a single function. So that's what we did. Using a particular measure that basically computes distances between distributions, we found that the best fitting function for the set of these normalized divisor volumes was this function here, p-fit, which you may recognize as the Wigner surmise, which tells you about level spacings in the Gaussian orthogonal ensemble. All right, so this is a crude fit for the normalized divisor volumes, but that's just for the normalized divisor volumes. To get a handle on how things scale with H11, we also need to fit for the mean of these divisor volumes. So that's what we did here. And so this is our simple model. And the question is this single distribution with this basic fit of the mean enough to capture all these complicated trends in stringy axion physics at large N that, we spent thousands of core hours getting a handle on via geometric computations? And the answer is that this simple model is enough, maybe somewhat surprisingly. So remember what I mean by our simple model. I mean that we take random draws from this p-fit distribution along with a regression on the logarithm of the divisor volumes. And we were able to reproduce axion phenomenology. Here I'm showing you one example of that where we can reproduce axion decay constants with this simple model. So here I'm showing you histograms of the decay constants across varying H11. In blue is the original decay constants that we computed in our full ensemble using all the tools of computational geometry. Where in orange is the reproduction of the axion decay constants that we get just by taking random draws from this simple function. And what we can see is that it does a pretty good job. And in fact, the model does better as you increase with H11. Okay, so I told you that more is different, but actually maybe the lesson is that more is the same. So what we've seen is that axion physics correlates with the number of axions in a given compactification in string theory. And this is driven by hierarchies in divisor volumes. But what we found is that actually distributions of normalized divisor volumes have some universal features as you go towards large H11. And because they have these universal features, we can approximate these distributions with a very crude model and use this model to reproduce stringy axion physics at large numbers of axions. All right, so I'm done. I just want to leave you with a set of questions kind of probing the future of this work. So what's next? Of course, the fact that this fit was the Wigner surmise is sort of tantalizing, and we'd all love a random matrix description of some aspect of Calabi-Yau geometry, and I wonder if this is hinting towards that, or is this just a crude fit for these distributions? Second of all, I want to understand whether we can generalize this sort of modeling to other classes of geometries. Does this give us a framework for understanding hierarchies of cycle volumes in G2 manifolds or Calabi-Yau threefolds that are not hypersurfaces and toric varieties, or even manifolds that are not Calabi-Yau at all? And can that help us to say something about axion physics in other kinds of compactifications? But of course, the real question that we want to work towards is whether some future observations, so some positive signal of an axion, can point us to the best weakly coupled description of our universe. That's the real driving question. And in that vein, I'd like to understand which observations constrain the axiverse the most. We have a whole host of various things that we can see: supernova, haloscopes, helioscopes, black hole superradiance, and we should understand which of these phenomena is the most constraining of the string landscape. And I'll just leave you with sort of a self-pep talk, which is that before an axion experiment returns a positive signal, let's determine the most precise statement that string theory can make about that signal. And with that, I will thank you.
Okay, thanks, Naomi, for a very clear talk.
axion-like particles. And yeah, so we studied for all the axion-like particles, things like the couplings of those axions to photons and their masses as well.
So this ratio of coupling over mass, does this change for axion-like particles with H11 as well, or do only the individual entries like change?
Yeah, that's something like what you would expect to get from the weak gravity conjecture or something like that, which is, I guess, what you have in mind. We haven't looked at it in extreme detail, but I wouldn't be surprised if there was some correlation like that.
Because that would be insensitive to the axion decay constant. So maybe that's
right.
Okay. Thank you.
Okay, I think in view of time, we can thank Naomi again.
So first of all, let me thank the organizers for inviting me to present our work here. This talk is based on a paper we put out last week with my collaborator Zhenchen Wang. And as you might be able to tell from the title and subtitle, this paper is pulled in two sort of different directions. On the one hand, our motivation and our source of inspiration comes from quantum gravity, but the main result of the paper is a formal reconstruction theorem in axiomatic quantum field theory. The relationship between these two things is inspirational. Gravity provides the questions we want to answer and the inspiration for the proof, whereas on the other hand, our theorem we can use to interpret in terms of quantum gravity and answer some questions. So I'd like to begin with some general comments about the gravitational path integral. First of all, in the quantum field theory path integral, we calculate physical quantities by an integral over local quantum fields. These are fields which can be cut and glued subject to a division of space-time into coordinate patches. And this cutting and gluing property makes the locality of the resulting quantum theory manifest. There's no mystery as to why the quantum field theory path integral produces a local system. This is not the case in the gravitational path integral. In the gravitational path integral, one fixes the boundary of space-time and integrates over all possible bulk manifolds. In general, there's no canonical division of the bulk of space-time into regions given a division of the boundary into coordinate patches. You might say that semi-classically, we do have such a division. We can associate each boundary region to its bulk entanglement wedge, but the entanglement wedges do not satisfy the correct cutting and gluing properties. In particular, the entanglement wedge of a disjoint union may be strictly larger than the disjoint unions of the entanglement wedges, as I've illustrated here. Of course, this is a feature of the gravitational path integral. This is not a bug. This is very important for the appearance of islands, as have played an important role in our understanding of the black hole information paradox. What it does mean, though, is that boundary locality, in other words, holography, is not manifest in the gravitational path integral. And so this leads to what's known as the factorization paradox, the tension between the absence of manifest boundary locality in the path integral, but the expected boundary locality of UV complete quantum gravity. The first issue associated with the factorization paradox is the issue of factorization of multi-boundary partition functions. This is the question that asks whether the partition function computed where the boundary of space-time is a disjoint union equals the product of the partition functions you would compute with one boundary or the other. The issue of partition function factorization is threatened by Euclidean wormholes. As I've illustrated, these are space-time manifolds in which two otherwise disjoint components of the boundary are connected through the bulk. The cross-section of a Euclidean wormhole, I should also say I'll always be in Euclidean signature, the cross-section is a state of a closed or baby universe. And it's this propagation of baby universes from one boundary to the other which leads to connected contributions and threatens the factorization of partition functions. Now, at least structurally, if not microscopically, I'd say we understand partition function factorization fairly well. We know that the necessary and sufficient condition for partition function factorization is that the Hilbert space of closed universes must be trivialized, must be one-dimensional, and in fact canonically identified with the complex numbers. When this happens, any propagation of baby universes is equivalent to no propagation of baby universes, and the multi-boundary partition functions are forced to factorize. Moreover, we know what happens when this breaks down. As explained by Coleman, as well as by Giddings, Strominger, Merolf, and Maxfield, any breakdown of partition function factorization is a red herring. At least given reflection positivity, we may always reinterpret this breakdown as the existence of an underlying ensemble of theories. In each of these members, called alpha sectors, we have a factorizing multi-boundary partition function, and the original partition function is recovered as the quenched ensemble average of these underlying partition functions. The basic argument at sort of a high level, maybe reinterpreted in modern language, we consider the algebra acting on the baby universe Hilbert space. This is the algebra generated by the d-dimensional components of the boundary of spacetime under disjoint union, subject to the gravitational constraints and completed appropriately. The key observation is that this algebra is commutative, and so the quantum mechanics of baby universes classicalizes. We can simultaneously diagonalize every observable, which means that we can replace quantum mechanics with classical probability theory. Now, you might hope that partition function factorization, once you project it to an alpha sector, is enough to get a holographic theory. However, this is not the case. The next question you have to ask is about the factorization of multi-boundary Hilbert spaces. Now I'm drawing a spatial slice of the bulk, and we ask, if we set up quantum gravity, where this boundary of a spatial slice is a disjoint union of two manifolds, does that Hilbert space equal the tensor product of the two one-boundary Hilbert spaces? Now, Hilbert space factorization is certainly threatened by Euclidean wormholes. If we have alpha sectors, the two sides need to be in the same alpha sector. But even if we only have a single alpha sector, this Hilbert space factorization may still break down. This is because it's also threatened by spatial wormholes or Einstein-Rosen bridges. Now, our expectation is that in the UV-complete theory of quantum gravity, Hilbert space factorization is resolved by the ER equals EPR conjecture, or at least the direction going from ER to EPR. In other words, the statement that every Einstein-Rosen bridge is equivalent modulo the gravitational constraints to a possibly entangled superposition of disconnected states. Structurally, Hilbert space factorization is less well understood. Until now, we haven't known a necessary and sufficient condition for Hilbert space factorization. And in general, it's been unclear what's happening when Hilbert space factorization fails. Now, this has been studied in a number of recent papers, and at least anecdotally, the pattern is that Hilbert spaces seem to factorize once you have enough degrees of freedom. Once your theory just has sort of enough generic degrees of freedom, the Hilbert spaces seem like they end up factorizing. It's worth noting, though, that we have known at least a necessary condition, if not a necessary and sufficient condition. This, I think, was first pointed out in Daniel Harlow's paper from 2015, which observes that Hilbert spaces, in order for Hilbert spaces to factorize, we necessarily need a complete spectrum of charged states. To illustrate this, consider Einstein-Maxwell theory without charged matter. In this theory, we have a two-sided Reisner-Nordstrom wormhole, and that wormhole cannot possibly live in the tensor product of the two one-sided Hilbert spaces if the one-sided Hilbert spaces have no charged states at all. Of course, they might sit in the tensor product of the microscopic Hilbert spaces in some UV completion, but it can't factorize in Einstein-Maxwell theory alone. This observation is related, of course, to the completeness hypothesis in the swampland program, as well as related swampland constraints like no global one-form symmetries and the triviality of cobordism classes. So Hilbert space factorization is the subject of this paper. It's the question we set out to answer. And in our paper, we give a full answer. We give a necessary and sufficient condition analogous to the triviality of the closed universe Hilbert space, and we explain what's happening when it breaks down in the same sense as Coleman. We explain the sense in which it's a red herring. So the basic conceptual idea of this project is to cut open the gravitational path integral in higher codimension. So we got the baby universe Hilbert space by cutting open the gravitational path integral in bulk codimension 1. We're going to now cut open the gravitational path integral in bulk codimension 2. And in general, when you have a quantum system and you cut it open in higher codimension, you expect to obtain not a Hilbert space, but a category. So what we obtain is a category, which I'll call the baby universe category, which you can think of as the category of Einstein-Rosen bridge sectors. So superselection sectors of Einstein-Rosen bridges, which cannot be cut. The necessary and sufficient condition for Hilbert space factorization is that the baby universe category is one-dimensional in the appropriate sense, meaning it's isomorphic to the category of, equivalent to the category of Hilbert spaces, having only one simple object and therefore no non-trivial superselection sectors. At this level, our construction is a formalization and retelling of some previous work. First of all, by Colafranceschi, Dong, Merolf, and my collaborator Wang, as well as a follow-up paper by Merolf and Zhang. So what is this category? So at a rough level, the objects are generated not by the closed d-dimensional boundaries of spacetime, but by the closed d-1 manifolds Bi. These are spatial slices of the boundary of spacetime. Generated, I mean, under formal direct sum and projection onto subobjects. The morphisms in this category are quantum superpositions of Bordisms. Bordism from B1 to B2 is a d-manifold which interpolates, takes you from one spatial slice to another, and I'm going to allow myself to take quantum superpositions. Therefore, this baby universe category is a quantum Bordism category, related to the Bordism groups of quantum gravity discussed in my paper with Kumran Vafa. Both the morphisms and the objects are subject to gravitational constraints. At the level of morphisms, this is the quotient by null states. At the level of objects, as we explained in the paper, this is encoded in what's known as the idempotent completion. So what we do in our paper, which is genuinely new from this previous work, is we consider the fusion in this baby universe category. We simply define the fusion of two d-1 manifolds to be their direct sum. This is very analogous to the algebra structure on the baby universe algebra. And again, our key observation is that this fusion is commutative, or more strictly speaking, is symmetric monoidal. And this means that this category classicalizes. It doesn't classicalize in terms of an ensemble. Instead, it classicalizes in a way that's described by what's known as the Doppler-Roberts reconstruction theorem. Rather than try to describe the Doppler-Roberts reconstruction theorem in general in this talk, I'm just going to describe the output of applying it to this baby universe category. And this output is our main theorem. So I'll now explain our main theorem. I should emphasize again that this is a rigorous theorem, mathematically rigorous theorem. It requires no assumptions about quantum gravity, either in its statement or its proof. So what do we do? What do we say? So I'm going to fix a class X of D manifolds. These can have sources or not have sources as you see fit. They may be Riemannian manifolds. They may have an orientation or a spin structure, maybe a background scalar field, background gauge field, or marked loci for operator insertions, whatever it is. And I'm going to assume I have a candidate partition function, meaning just some abstract function on the class of closed D manifolds with X structure, and it's just a complex number for every closed manifold. And I'm going to assume that zeta satisfies the axioms of this previous work, CDMW. This means that it's finite on a closed manifold, it's continuous as a function of sources, and it satisfies a number of basic kinematic axioms. For instance, it takes the orientation reversal to the complex conjugate, it's multiplicative on disjoint unions, and it takes the empty manifold to the number 1. I should comment on the multiplicativity assumption. This is sequestering the issue of partition function factorization. I'll explain at the end of the talk how to do both at once, but I'm going to assume we're already have factorizing partition functions. The final axiom, and in many ways the most important, most non-trivial assumption, is reflection positivity. This is the statement that if you only know the closed manifold partition function, even if you don't know that it came from a quantum field theory in any way, it's just a function, you can still infer what the inner product would be on states prepared by manifolds in an underlying quantum field theory. So what do? I fix a spatial slice B, and I think about preparing states by cut manifolds on B. I can glue any two such manifolds with boundary B together into a closed manifold, evaluate it using the partition function, and demand that all sesquilinear combinations of this be non-negative. Again, I should emphasize this requires no assumptions about the properties of the partition function, no assumption that it's prepared by integrating, evolving into a Hilbert space and then evolving further, because I'm only evaluating it on closed manifolds. So those are our assumptions, and our conclusion is that there exists a local, unitary, compact quantum field theory with partition function zeta. So I took a lot of, I was very careful to not assume that I have a quantum field theory, but the output is that I actually do. Specifically, the notion of quantum field theory we use is very similar to the notion of Kontsevich and Siegel. The second part of our theorem says that any two such quantum field theories are unitarily isomorphic. In other words, what we prove in parts A and B is that unitary quantum field theories in general are determined by their closed manifold partition function. This is true both in the sense that if you have a quantum field theory and you give me its closed manifold partition function, I can reconstruct it, and in the stronger sense that if I just have an abstract function which satisfies our axioms, then I can get a quantum field theory. In particular, as an aside, this resolves the conjecture from almost 40 years ago of Friedan and Schenker, which asks whether two-dimensional conformal field theories are determined by their all-genus partition function. Our theorem implies that they are. I should also emphasize that we do not assume any properties of the partition function at the boundaries of moduli space, for instance, in degeneration limits. We only assume, the key assumption is reflection positivity. And the last part of the theorem says that if we fix such a quantum field theory, and we consider the symmetry group, which is the maximal symmetry group of that underlying quantum field theory, for which all sources are neutral, then a state in a Hilbert space can be prepared by evolution over Euclidean X manifolds if and only if it's invariant under G. So one direction is obvious. I define G to be the symmetry under which these manifolds are neutral, so clearly I can't produce any charged states. The non-trivial claim is that I can produce every neutral state, at least by linear combinations and limits. So I'll now apply this theorem to the gravitational path integral. I'm going to take my class of manifolds, X. I'm going to imagine it that it's the collection of all possible sources for a gravitational path integral. Whatever bulk fields I may think I have, I turn on sources for those fields on the boundary. And I'll take zeta to be not the output of the gravitational path integral itself, but an alpha sector partition function, so it factorizes. And making a very big assumption, which is reflection positivity, I should comment that a generic gravitational path integral probably does not produce a reflection positive partition function. We've seen this in a number of recent papers, even in many places. But of course, it's required if we're going to have a unitary theory of quantum gravity at the end of the day. So assuming reflection positivity, then the Hilbert spaces obtained by cutting open the gravitational path integral are just the Hilbert spaces of states preparable by Euclidean X manifolds. These are the states which can be prepared by the gravitational path integral, and if I've turned on sources for all bulk fields, then they're also the sort of Hilbert spaces of the bulk effective field theory. And what we show is that these Hilbert spaces can be isometrically embedded in the Hilbert spaces of an underlying quantum field theory in an essentially unique way. I map a state prepared by a manifold, a formal state prepared by a manifold, to the actual state prepared by a path integral over that manifold. And what do we conclude? Well, if I consider the symmetry group, G, which is the maximal symmetry group under which all of my sources are neutral, but also my bulk states are all neutral, then the multi-boundary non-factorizing Hilbert spaces produced by the gravitational path integral are simply the G invariant states in the underlying quantum field theory. In other words, I show that the necessary condition of Harlow's paper is also sufficient. And so given reflection positivity, completeness of the spectrum is equivalent to Hilbert space factorization. The implication goes in both directions. I should also comment that this formula is very similar to the formula I wrote before for the multi-boundary partition function. It's what I might call a higher ensemble average. I don't average over a family of theories. I have one theory, but I average the states over the action of the symmetry group. This also makes it clear why they don't factorize, because a G invariant state in a tensor product need not be the tensor product of G invariant states. So the reaction I've been getting this week when I tell people what our claim is that this theorem is either obvious or false. So I thought I'd give you a very simple example where you can see how everything works. And in many ways, this example contains the essence of the general proof. So this example is in D equals 1. My manifolds will be oriented and topological. This means that I'm considering topological bosonic quantum mechanics without time reversal symmetry. This theory is determined by a single number. This is the partition function on a circle, and it's some number k. By my kinematic assumptions, it needs to be real, and by a simple application of reflection positivity, it must be non-negative. But in order for this to be the partition function of topological quantum mechanics, k needs to be a non-negative integer, in which case we can take the Hilbert space on the point to be c to the k. This theory is unique when it exists, because every k-dimensional Hilbert space is unitarily isomorphic to every other one. Incredibly, reflection positivity actually does imply that k is a non-negative integer. The argument, this is an argument which appears in the proof of the Doppler-Roberts reconstruction theorem. It appears in Deligne's proof of his theorem on tensor categories, and it also appears in this motivating work of Cola-Franceschi, Dong, Meroff, and Wang. So what do? So I consider two n-points, n of which have positive orientation and n of which have negative orientation. And I prepare a state which is associated, if you like, to the formal projector onto the nth antisymmetric tensor power. By this I mean the following. I start with 1 over n factorial, and then I sum over elements of the symmetric group. So for every permutation of n, I have a geometric state prepared by n semicircles, where the semicircles connect the ith negatively oriented point to the sigma ith positively oriented point. I weight them by the sign, and I compute the squared norm of this state. It's a simple exercise in combinatorics to compute the squared norm. It's the formal dimension of the nth antisymmetric tensor power of what the Hilbert space would be, by which I mean it's k choose n, which again I mean the falling power k times k minus 1 down to k minus n plus 1 over n factorial. But this is the squared norm of a state. And so by reflection positivity, it had better be a non-negative number for all n. And in order for this to be non-negative for all n, k has to be an integer. The reason for this is that if k were not an integer, then as soon as n exceeds k by a little bit, this falling power would become negative. And the only way out is if k is an integer and this falling power becomes 0 and then remains 0 forever. In the language of Deligne's framework, you would say that this object needs to be annihilated by a Schur functor. I'm not going to spell out the details, but Schur-Weil duality actually implies that all of the geometric states in this theory are precisely the UK invariant states in the underlying topological quantum mechanics, where UK is the symmetry which rotates the k-dimensional space of degenerate ground states. This was shown in a beautiful paper of Henry Maxfield in the context of quantum gravity, and it's also the underlying observation corresponding to Deligne and Milne's categories called rep GLT. So I'll start wrapping up. To reiterate, what I've shown is that any breakdown of Hilbert space factorization is a red herring. By this I mean that if you think you have non-factorizing Hilbert spaces, then you can always embed them in the Hilbert spaces of a uniquely defined underlying quantum field theory and reinterpret the original breakdown as the result of having averaged your states over the action of a symmetry group. In a precise sense, the embedding of your theory into the underlying quantum field theory is the analog of projecting to an alpha sector. For most of my talk, I've assumed that I was working in a single alpha sector, but it's not hard to handle both partition function and Hilbert space factorization at the same time. If we have alpha sectors, then the tensor unit of the baby universe category, its endomorphism algebra, will be the baby universe algebra. And so it contains the previous story of alpha sectors. And the formula we get is just the direct integral of the previous formula over this collection of alpha sectors. An important subtlety is that if the different alpha sectors have different symmetry groups, then this group G alpha can get washed out in the ensemble. One place this happens is in the example of Meroff and Maxfield. In their alpha sectors, we have symmetry group UK, just as in the topological quantum mechanics. But this UK symmetry group gets washed out in the ensemble. You don't see any UK gauge fields propagating in the bulk. You do, in fact, see the diagonal U1. The diagonal U1 is associated to the cobordism symmetry, and it's related to the completeness of end-of-the-world branes. The U1 survives because it's in every member of the ensemble. This also means that the notion of completeness I'm using is maybe a little bit more general than completeness is usually considered in effective field theory. It's completeness with respect to the global symmetry group of the microscopic holographic dual, which may or may not be visible from the start as gauge fields in the bulk. And I'd like to end by looking forward. So I've built this baby universe category in this paper, It's the category you obtain when you cut the bulk in bulk codimension 2 through a cut that does not extend out to the boundary. But of course, you should cut the bulk in codimension 2 also in cuts which do extend out to the boundary. And we should define some associated category to non-empty boundary codimension 2 manifolds, D minus 2 manifolds K. So we would build this category, and we can then ask, does the category associated to a disjoint union of two boundary D minus 2 manifolds tensor factorize as the tensor product of the two categories you'd assign to each side at once? This question of factorization of categories is related to the completeness of the spectrum of charged strings and the absence of global two-form symmetries. And of course, we should keep going, that we should consider the factorization problems related to absence of global p-form symmetries for all p, or in other words, factorization for handles of the bulk spacetime of all dimension. If we could complete that program, it would require some analysis that has not been fully developed. You'd have to work with type 3 von Neumann algebras and really get into some hard problems. But if you could do that, you would eventually be able to discover full boundary locality, in other words, holography. So thank you for listening, and I look forward to your questions.
Okay, thank you, Jake. There's a question over there by Hiroshi.
What about fermions?
Sorry?
What about fermions?
Great question. So we discussed fermions at length in the paper. In the most naive way of building this category, we can handle spin structures, but we can't handle fermionic sources. This is because fermionic fields should anti-commute at space-like separation and not commute, which means you can't work with a symmetric monoidal category. And we also provide a way of remedying this, which is to work with a supervect-enriched symmetric monoidal category. And so it works. In fact, in some sense, that version is more natural in the first place anyway. It's like working with the complex numbers as opposed to the real numbers.
Okay. So this is sort of clarification further to the question. So you started with your main theorem stating that you're considering class of compact manifold with or without sources. Can you state the theorem by restricting yourself without sources? And if the answer is yes, can you reproduce property of operators in that theory in practice, not in principle?
Well, maybe I should first answer in principle. If I have a conformal field theory, what we reproduce is the Hilbert spaces and the Euclidean evolution operators along bordisms. And so for a CFT, we reproduce all correlation functions of local operators through the use of the state operator correspondence. In practice, it's probably pretty hard. Up to the point of constructing the baby universe category, everything is constructive. If you have enough computational power, you can build these bordisms. Finding the underlying quantum field theory from there is not so hard either. But really the hard part is finding the reflection positive partition function in the first place. I think it's going to be very hard to find that without maybe already knowing the answer.
Thank you. Very, very interesting theory.
Thank you.
Emil?
Hi, Jake. Yeah, I just wanted to comment that it's an important input to this theorem that the partition function actually is well defined.
Yes, of course.
And as far as I know, that's only true for topological theories in 0 plus 1 or 1 plus 1 dimensions. You know, even with JT, the sum over topology gets you in trouble, and of course, in higher dimensions, there's non-renormalizability. So, yeah, what do you view as the setting for this theorem, or do you think there could be like an EFT version of this theorem or something?
Yeah, I would really like there to be an EFT version. I'm not sure whether you really can. I motivated this from the gravitational path integral, but as you point out, the gravitational path integral is probably not computable in higher dimension.
Or definable.
Well, what I will say is that I think it's probably reasonable to believe that UV complete quantum gravity, whatever it is, has boundary conditions, well-defined boundary conditions, and for each boundary condition has a partition, like a finite number well-defined partition function. But yeah, the application to EFT would be very nice, very helpful.
Juan?
Can I view this theorem as justifying a bootstrap problem where you try to bootstrap this correlator? This is sort of partition function.
Yes, and in fact, from a bootstrap perspective, our theorem says that the reflection positivity of the closed manifold partition function is a complete bootstrap. It's a complete set of bootstrap constraints, in the same sense as like in a 2D CFT, the 4-point function and torus 1-point function is a complete set. This says if you can prove reflection positivity of the closed manifold partition function, you're done.
Hi, thanks for a nice talk. Can you say some words about the groups G that generically appear? Like, are they infinite dimensional? How badly behaved are they?
Yeah, so the group G, what comes out of the Doppler-Roberts reconstruction theorem is a compact Hausdorff group. However, the only example I know where it's not a Lie group is a sort of degenerate example, which is quantum mechanics with infinitely many energy levels. The group you get is the product of the unitary group over every energy level, but this is special to quantum mechanics because commuting with the Hamiltonian is much less constrained than commuting with the stress tensor. So I probably expect outside of that example, you get a compact Lie group.
Okay, maybe I also have a quick question since we have a minute. By this G average, you mean gauging or projecting to G invariant states?
I mean project to G invariant states.
So not gauging, so this is not a local...
Great, yes. If I had written G invariants for each tensor factor and then also included twisted sectors, this would be gauging. I would say that this is a quenched version of gauging. Gauging is the annealed version where you gauge on each component. This is the quenched version where I tensor the Hilbert spaces first and then gauge. It's like the difference between a decomposing theory and an ensemble.
Okay, let's thank Jake again.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
I feel very visible. Still have 2 minutes.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Okay, 大家好. It's a pleasure. 谢谢, 谢谢. It's a pleasure to have Edward Whitten here, who's going to tell us about comments on errors in entanglement wedge reconstruction, which makes me a little nervous because I worked on entanglement wedge reconstruction.
Thank you. Thank you, and thanks to the organizers of this marvelous meeting for putting it together and inviting us here to Shanghai. And if they could do us one more favor by putting off the typhoon just a little bit till we all safely leave, that would be appreciated. So entanglement wedge reconstruction is an important part of the way we understand holography. So in holography, we have a bulk space-time, schematically this disk, and then there's a boundary where an observer is somehow reconstructing the interior. And entanglement wedge reconstruction says that if you have access only to a region A of the boundary or a region A bar, then what you can reconstruct is the portion of space-time up to the RT surface. So as I just said, a boundary observer with access to the region A of the boundary can reconstruct the bulk physics in an entanglement wedge, little a, bounded by the RT surface. Now, our session chair for today showed, under certain assumptions that we'll discuss, that if entanglement wedge reconstruction is exact, then the area of the RT surface does not depend on the state of the bulk quantum fields, which you could roughly describe by saying that there's no gravitational back reaction. In other words, if there are particles in the bulk, they have gravitational fields, they change the metric, and you'd expect them to change the area of the RT surface since they would change generically all areas. And there were all kinds of RT surfaces because we could have picked any area, any region, capital A we wanted on the boundary. So it's unsatisfactory to believe that the state of the bulk fields does not affect the area of the RT surface, and that suggests that entanglement wedge reconstruction should not be exact. Proofs of entanglement wedge reconstruction are, like proofs of the RT formula, are based on semi-classical gravitational path integrals, so one doesn't really expect it to be exact, but one would hope that it's exact to all orders of perturbation theory because that's the validity of semi-classical calculations. Now, a setup that leads to exact entanglement wedge reconstruction is very restrictive. So divide the boundary as in the picture into two complementary regions, A and A bar. Similarly, divide the bulk into two regions, little a and little a bar. For simplicity, assume the CFT Hilbert space factorizes as a tensor product. Okay. It's a tensor product of the Hilbert space of region A and Hilbert space of region A bar. Similarly, let H sub L be the low energy bulk Hilbert space and factorize it as L little a times L little a bar. So holography is interpreted to determine isomorphisms between LA and LA bar and subspaces of HA and HA bar. So we further, for simplicity, will assume decompositions that HA is the tensor product of a low energy part that's isomorphic to the bulk Hilbert space and some high energy part that we don't know much about, but that somehow is presumed to be responsible for the area term in the RT formula. Similarly for HA bar. So HA2 and HA bar 2 contain the short distance modes that are presumed to be responsible for the Bekenstein-Hawking entropy, in this case of the RT surface. Then consider a state psi in the Hilbert space HL of the low energy degrees of freedom in the bulk. So if you're strict to bulk regions little a or little a bar, it would have density matrices sigma a and sigma a bar. And ADS-CFT duality is presumed to involve an embedding of the low energy Hilbert space HL in the Hilbert space H of the CFT. So it's a map from the low energy bulk degrees of freedom to the CFT Hilbert space. And exact entanglement wedge reconstruction is possible if and only if V has a very special form. The map from low energies to the CFT Hilbert space. Sorry, I find the difference between up and down on this controller to be confusing. That's why I can keep going in the wrong direction. Psi should map to itself, tensored with some state of the high energy degrees of freedom, but encoded by unitary operators, one in region A and one in region A bar. So that very special situation, as was essentially shown by Harlow in a paper I mentioned at the beginning, is the setup in which entanglement wedge reconstruction is exact. So chi is some fixed state of the high energy degrees of freedom. Now, exact entanglement wedge reconstruction means that exact entanglement wedge reconstruction means that a boundary observer in region A, by acting on the CFT state, V of psi, with the unitary operator UA that acts only in the observer A's part of the Hilbert space HA, can recover the density matrix of the bulk region little a. The way it works here is the following for the case of exact reconstruction. If the encoding of the bulk state psi in the boundary state V of psi is just given by this simple formula, the boundary observer can undo the encoding by acting with the unitary transformation RA to get this state. And then the density matrix of that state in region A is the bulk density matrix that the observer wanted to reconstruct, tensored with a projection onto the state chi. So in other words, the observer has reconstructed the state of the bulk fields, tensored with a fixed state of the short distance degrees of freedom. So that's the basic setup in which entanglement wedge reconstruction is exact. Now, Harlow also showed this setup leads to a version of the RT formula for the entropy capital SA of the density matrix sigma A. With the density matrix, CFT density matrix in region A being this, its entropy is the entropy of the bulk degrees of freedom plus the entropy of this state chi restricted to A. I should have, here, this should be projected onto region A. And that's a version of the RT formula, except that it has the property, okay. The RT formula says that the boundary entropy is the bulk entropy plus the area. The point I'm going to make in the rest of this talk is that in the CCKLP setup, this is what happens, provided the geometric entropy is of order 1 over G compared to the bulk entropy, then the deviation from exact entanglement wedge reconstruction is exponentially small compared to back reaction. Now, in analyzing this, first of all, we can replace this encoding by a more convenient version in which we act on the left with RA bar, which if W were 1 would undo the effect of the encoding by these local unitaries. We can do this because we're anyway supposed to optimize over the optimal reconstruction that the observers can make, which involves acting on the left with local unitaries. And since we're anyway supposed to average over optimize over the choice of local unitaries, RA and RA bar can be absorbed in this optimization that we are anyway planning to do, although actually doing it turns out to be unimportant for what I'll say. So we could replace this with this. And since W is drawn from an ensemble that's invariant under conjugation by a unitary matrix, we can replace this thing, which is W conjugated by this unitary matrix, with just e to the epsilon W. So to explore the consequence of a generic small violation of entanglement wedge reconstruction, we can consider the family of encodings where you do nothing except tensor with some fixed state of high energy modes, and then you make a generic small correction to it by unitary. So that's a very simple family of things to analyze. To explain heuristically why the violation of entanglement wedge reconstruction is much less than the gravitational back reaction, well, first recall the definition of the relative entropy between two density matrices, which I've written the standard definition here. And one term is minus the entropy of sigma tilde, and the other term is minus the trace of sigma tilde times log sigma. Now, So now, for this state, we can take its density matrix in either region A or region A bar. So I'll write sigma A epsilon for the density matrix of A when epsilon isn't 0. And similarly, sigma A1 for the trace of this over A2. At epsilon equals 0, they satisfy a very simple relation. So the density matrix of the full boundary region A is a tensor product of a density matrix of the low energy degrees of freedom times a fixed state of the high energy degrees of freedom. And similarly, that carries over to logarithms. The logarithm of A1, A2 is the sum of logarithms. And if you combine the formulas on the last slide, you find that what was called the pseudo-entropy, the geometrical entropy by CCKLP, is mostly a difference of relative entropies with one leftover term. And although you can analyze this in general, to give you the flavor, I'm going to assume that the high energy states are in a maximally mixed state. That leads to a simplification because in that case, this extra term is just the entropy of the state chi. It's just the area term in the RT formula. It doesn't depend on the state of low energy quantum fields. In general, you could show that this term doesn't depend very much on the state of low energy quantum fields, but that's a longer calculation. But if the high energy modes are maximally mixed, then this thing is simply equal to S chi, the area term in the RT formula at epsilon equals 0. So in that case, the geometric entropy of CKLP is just a constant, the area term in the exact case, plus a difference of relative entropies. So since S chi is a constant, the gravitational back reaction is given by the last two terms, a difference of relative entropies. Now, recall that the importance of relative entropy is that it's a measure of the difference between two density matrices, or two quantum states. In particular, this one measures the difference between the density matrices of the full region A equals A1, A2, at epsilon equals 0 or at non-zero epsilon. And the other one measures the difference between the same two density matrices after tracing out A2. Now, in gravity, we want the dimension of the low energy Hilbert space. We want to think of that as being large but independent of G, while the dimension of the high energy Hilbert space is exponentially large of order e to a constant over g to account for the fact that the area term in the RT formula is of order 1 over g. So in other words, for gravity, we want to think that 1 is much less than the dimension of the low energy Hilbert space, but that's exponentially less than the dimension of the high energy Hilbert space. Now that suggests that the relative entropy, you see, we're comparing two different relative entropies. We're comparing the relative entropy of the same two quantum states, sigma epsilon and sigma 0. In one case, we're comparing the relative entropies, sorry, sorry, I keep getting confused with using this device. Sorry. Let me go back to where I was talking. On the left or right, we're measuring the difference between the same two the same two quantum states. But on the left, we're measuring the difference after forgetting most of the state. So on the right, we're comparing the exact embedding at epsilon equals 0 to the twisted one when epsilon isn't 0 in the full region A. But on the left, we're comparing the same two things, but only for the low energy part of the state A1. So that suggests that the relative entropy on the left is much less than the one on the right. And a detailed calculation indeed shows that the relative entropy on the left is of order d1 squared, the one on the right is of order d1 squared, d2 squared. Now, the larger of the two is the gravitational back reaction in the CCKLP setup. But the one on the left, the small one, is a measure of the error in entanglement wedge reconstruction. Because it literally, for this one, entanglement wedge reconstruction is exact, and the difference between this one therefore tells us how much entanglement wedge reconstruction will fail to be exact for the perturbed state at non-zero epsilon. So, although it's true that the gravitational back reaction is a difference, the second term is completely negligible compared to the first. If we adjust the parameters of the model so that gravitational back reaction is of order 1, then the small term is exponentially small. And as I said, the small term is an error, a measurement of the error in entanglement wedge reconstruction, and its smallness means those errors are exponentially small. So that's the promised result. So, in sum, CCKLP considered a generic perturbation of a model with exact entanglement wedge reconstruction. If the parameters are adjusted in their model to make gravitational back reaction of order 1, then the violations of entanglement wedge reconstruction are exponentially small as expected in gravity. Thank you.
I'm reminded that in physics time goes up, but in Chinese it goes down.
Well, I was more successful Tuesday, I think, in using this device in the right direction, but today I got confused.
So let's take a question from the audience. Anyone? Maybe here? Is that?
Yes, at least one, I see.
Thank you for nice talk. I think it is very it really depend on the whether you fix the epsilon or epsilon is taken to be like a scaling with G Newton or not.
Oh yes, so we have to scale epsilon with G Newton to make the gravitational back reaction of order 1.
Mm-hmm.
So the way I phrased it was that if we adjust the model so that gravitational back reaction is of order 1, then the failure of entanglement wedge reconstruction is exponentially small.
Mm-hmm. So So can you remind me again? So you take epsilon to be order 1 or?
Epsilon is exponentially small.
Exponentially small in
and
G Newton.
The failure of gravitational back reaction is exponentially small.
Mm-hmm.
But the back reaction on the area of the RT surface is of order 1.
Okay, thank you.
Yeah, okay. Let's see if there are more questions before I say anything else.
We can maybe do one more quick one, and then we should keep going.
I see at least one in the back.
In the back? Is that Alexei? I can. Yeah.
So, does your computation say anything about the amount of magic in gravitational states?
I didn't investigate the amount of magic. That was an important point in the article of CCKLP, but, well, one could investigate it in this region. I expect there's a lot of magic in a realistic holographic state.
Okay, I think we should probably stay on schedule, so let's thank Edward again. They'll deal with it. Okay, are you ready? Okay, so let me say, it's a pleasure. So it's a pleasure to have Shai Chester here from ICL to tell us about worldsheet bootstrap meets string field theory.
Thanks so much for the organizers. This is definitely the most chandeliers I've ever seen in one room, so it's exciting to be here. This is based on work in progress with Fernando Alday, Kiarash Naderi, Deliang Zhang. Kiarash is my postdoc. Deliang was my postdoc. He is now faculty here in China. All right, so this talk is about string theory in curved spacetime. String theory in curved spacetime, such as ADS, usually requires Ramon-Ramon flux. But one of the biggest problems in string theory to date is that it's very hard to use the textbook version of string theory, which is what we call RNS string theory, like that's what you would find, for instance, in Polchitsky, to study Ramon-Ramon flux. And so this is why there has not been as much progress as perhaps we would want in applying string theory to the real world, because in the real world, we do have curved spacetime, for instance in cosmology, and we just can't do that with string theory as it's traditionally understood. So this is, I would say, in my opinion, one of the biggest open problems in string theory. So some progress has been made at tree-level string theory using the method of integrability, which I'll discuss a bit later in the talk. But that progress has been much more limited in the case of ADS3, which is perhaps surprising, because naively you would think that the smaller the dimension, the easier problems are, but it turns out actually that ADS3 is harder than higher dimensions. So in today's talk, we're going to discuss two methods that allow one to, in general, address the problem of string theory in ADS, and we will apply them in particular to the case of ADS3. So the first method is the worldsheet bootstrap, which I will explain in the coming slides. I think of this as a bottom-up method. It's based on kind of general principles. And then the second method is string field theory, for which we've already heard a couple talks before. And this is a top-down method in that you have an explicit string theory, and then you are applying it to this problem of ADS. Okay, so a brief review of ADS-CFT. So in this talk, we're going to consider the most classic examples of ADS-CFT. That is Type 2b string theory in ADS5 crosses 5, dual to n equals 4 super Yang-Mills. Type 2a string theory in ADS4 cross CP3, dual to ABGM theory. And finally, 2b string theory in ADS3 crosses 3, cross M4, where M4 is some four-dimensional manifold we'll discuss later. And this is dual to a somewhat more mysterious two-dimensional CFT called the D1-D5 CFT. So the basic input of this duality is that we are considering tree-level string theory, so leading order in G string, but the answers are for finite alpha prime, also known as string length. And in the duality, this is dual to the planar limit of the CFT, so where n goes to infinity, where n is some parameter which appears in all these CFTs, but it is for finite lambda. So lambda is basically the analog of the Tuft coupling. In n equals 4 super Yang-Mills, it's precisely the Tuft coupling, but you can always define an analogous quantity in any of these examples. The precise definition is just in terms of the ADS radius L and the string length. So we're only going to be working at tree level, so the whole talk will be planar limit. one could look at different regimes of lambda. So when lambda is very big, then you see the ADS radius goes to infinity. This is flat space string theory. On the CFT side, this is strongly coupled. So it's usually hard to do calculations from the CFT perspective. Usually it's much easier in the opposite limit. So when lambda goes to 0, then that corresponds to weak coupling. And so for the cases of ABGM and n equals 4, then we have everything under control because we have a very simple Lagrangian and we can just compute things using Feynman diagrams. Unfortunately, though, in the 2D case, this D1, D5 CFT is much more mysterious. And in the limit where lambda goes to 0, actually, it's actually quite hard to study, as we will see in the talk. And so that's why we have less control. Okay, so a brief comment about integrability. If anyone is ever talking about doing string theory in ADS, the most obvious thing you would think of is integrability, especially at tree level. So the idea of integrability is that instead of using the RNS formalism, which can't handle remote flux, instead you have the Green-Schwarz string, which you could think of as kind of an effective theory, because we don't really know how to quantize it in general, but classically it works just fine. And the advantage is that you can do it on any manifold you want, so you can do it with remote flux. Another aspect of integrability is that the dual CFT was also shown to be integrable in a very long story involving many authors who unfortunately I don't have space to credit all of them. So kind of from going from both directions, from the Green-Schwarz string from one direction and from the explicit dual CFT from the other direction, ultimately this led to something called the quantum spectral curve, which is this amazing method which allows you to compute the scaling dimensions of all operators in the theory, in the planar limit, but for any value of this tough coupling lambda. So in the case, this was first done for n equals 4 super Yang-Mills in this foundational paper. It was done several months later by some of the same authors in the case of ABGM. And in both of these cases, they were able to do it because they knew the CFT very explicitly, and they were able to combine that with the string theory. So as an example of one of the things that could be learned once you know all the scaling dimensions for any lambda is that in particular, you could look at large lambda. Now, I will emphasize that the way you solve this quantum spectral curve, it's a numerical thing. So it's actually quite complicated. So it's not just like you can analytically do large lambda. Instead, you numerically solve it at large lambda. You do a fit. So for instance, for the lowest Regge trajectory, for instance, when spin is 0, this would be the Konishi operator in n equals 4 super Yang-Mills, you can read off this answer for the scaling dimension, where this power of lambda to the quarter that's kind of expected from string theory based on dimensional analysis, and then it's kind of an expansion in 1 over square root of lambda with the exception of the first term, minus 2. And in fact, they even went to higher orders in 1 over lambda. On the other hand, it has been much harder to derive this quantum spectral curve in the ADS3 dual to 2D CFT case. And that's basically, there's many reasons why, but one such reason is that much less is understood about the 2D CFT. And so you can't kind of work from both sides now. Nonetheless, it turns out that the form of the quantum spectral curve is so rigid that these very clever people were able to basically guess an answer a few years ago, but this is quite conjectural, it's certainly not derived. And even after they guessed the answer, to actually solve it in practice was even more difficult. And so it's only actually in the last few months that they've been able to actually numerically solve this conjectured quantum spectral curve to get some large lambda results for a specific class of states. So basically, I'm just trying to emphasize that integrability in ADS3 is much harder and much less understood than the higher dimension cases. And in general, for integrability in any dimension, so far people only have scaling dimensions. And so people don't know how to get OP coefficients except for very special classes of states in limits where their R charge goes to infinity or something like that. But for standard states like the Konishi, it is unknown how to get OP coefficients. Okay, so that was the brief review of integrability. Now I'm going to tell you what the worldsheet bootstrap is, which is one of the main heroes of this story. So the worldsheet bootstrap applies to 4-point functions. That's kind of its natural object. So we consider a correlator of a CFT operator O, which is dual to some graviton mode in ADS. I'm trying to be general here, because this applies in general dimensions. So as usual with conformal symmetry, you factor out H of U and V, where U and V are conformal cross ratios. You can then expand the correlator in superblocks. So you are thus now imposing supersymmetry, which occurs in every example of holography we deal with. In practice, what this means is that you have superblocks, which are linear combinations of conformal blocks, which correspond to different supermultiplets. And the interesting multiplets are the unprotected multiplets. There's also protected multiplets, but those are less interesting, and so I don't really write them explicitly. The reason why they're less interesting is that their scaling dimensions are fixed. So in the limit we're going to consider, which is large tough coupling, they basically decouple. Okay, so this is all kinematics so far, and totally non-perturbative. If we now want to restrict to large N, it is useful to consider something called the Mellin transform. The Mellin transform is basically just a Fourier transform which respects conformal symmetry. So that's the formula you see here. It's a Fourier transform from conformal cross ratios U and V to some other variables called S and T. But there's this funny factor of gammas here. Now, why do we put these gammas here? The reason is that poles in variables S, T, and U, where U is just related to S and T like this, they correspond to the scaling dimensions of operators that are being exchanged. So if we now think of the CFT correlator from the bulk perspective, computing Witten diagrams, you have exchange Witten diagrams, and their scaling dimensions correspond to these poles. And so a convenient trick to take into account the exchange of double trace operators is to insert these gammas, because these gammas are functions which are basically defined such that they have poles at every value of double trace operators. And so that just simplifies the resulting formula for M of S and T, which is our Mellin amplitude. So in particular, if we're working in the planar large N limit, then the only exchanges we would have are double trace and single trace. The double traces are all taken into account by these gammas, so we only really have to consider single trace exchanges, and there's a very small number of such single trace exchanges for a given correlator. So for instance, if we are considering the correlator of the stress tensor multiplet, there's only one single trace exchange that occurs, which is the stress tensor multiplet itself, which is dual to supergravity. And so for instance, this Mellin amplitude at leading order at large N, it will have the first term due to supergravity, which is meromorphic in S and T, so it just has a couple poles. And then all the other terms which you see here, these correspond to contact terms in the bulk, and kind of all the interesting dependencies in these contact terms. So this is an expansion in the Tufts coupling, and determining the coefficients of this expansion would basically tell you everything about this correlator at tree level. And so the goal would be to kind of determine these explicit polynomials P. Okay, so that's all just kind of definitions and kinematics. Now this is where it gets interesting. So we're talking about a holographic correlator in ADS. So there should be a way of making the ADS radius go to infinity, such that we get back a flat space amplitude. And indeed there is a way, and this was shown to us by Penedonis, I guess 15 years ago at this point. And this shows another advantage of the Mellin formalism. So the idea is that you take your 4-point function, as written in Mellin space, you rescale the Mellin variables S and T, you take a Borel transform, which is what this integral is, and then you make this Tufts coupling go to infinity. Remember, the Tufts coupling is related to the ADS radius. So, and lo and behold, you get your flat space amplitude. And so this is just proven in his paper. So this is just a proven fact that this gives the expected flat space amplitude. Now I will start with the worldsheet bootstrap. So what the worldsheet bootstrap does, it consists of two assumptions. The first assumption is that this flat space limit formula, which is rigorous in the strict flat space limit, also defines a reasonable ADS amplitude as an expansion around flat space. So I define these A1s, A2s, A3s, etc., to be down by powers of 1 over lambda, which is the ADS radius, as corrections to the flat space amplitude. Now, what do I mean by reasonable? Basically, you will see in the next couple slides that it gives answers consistent with integrability and other methods. So that's the first assumption. So now that we have made that assumption, we can now go ahead and just take the CFD data that appears in our 4-point function, which are various unprotected multiplets corresponding to single trace operators, and we can just expand them at large lambda. So we choose to label our operators by their spin, as well as some labeled delta, where delta goes like 1, 2, 3, 4. You'll see in a moment what the motivation for this delta. And so this is our spectrum of operators. They're expanded at large lambda. So in general, tau is the twist, which is the difference between the scaling dimension and the spin. So this twist, it has an expansion in lambda to the quarter, just as we saw for the Konishi a few slides ago from what you get from integrability. The corresponding OP coefficient also has an expansion at large lambda. There's this kind of funny factor of sine squared, but that just comes from applying this Borel transform to the block expansion. So the idea is that we take our 4-point function, expand it in blocks, and then if we want to start expanding around flat space, we just apply this Borel transform to the block expansion. And so if you do that, you find that your 4-point function now in this flat space expansion takes the following form. So you have your OP coefficient squared as normal. It's an expansion in 1 over lambda. And then there's these functions R, which include all the non-trivial information, which have simple poles in S and T. Okay, so this is the first step of the worldsheet bootstrap program. It's just the block expansion expanded in ADS around flat space. So for instance, the strict flat space limit, the amplitude is just the Virasoro-Shapiro amplitude, because we're talking about scattering of closed string states. And so as written as a worldsheet integral, this takes this standard form here. Now for the second assumption. So this comes from the foundational paper by Fernando, Tobias, and João from 2023. So the second assumption of the worldsheet bootstrap program is that you assume that your corrections to the 4-point function into ADS from flat space are given by a worldsheet integral of a specific form. Now, generically, you would probably expect a worldsheet integral because, after all, this is supposed to be string theory, so things are supposed to be worldsheet integrals. After all, the flat space answer, of course, is a worldsheet integral given here. But the magic here is your ansatz for the integrand of that worldsheet integral. And so it's the following ansatz. Here I'm showing the first correction, but there's an analogous ansatz for higher corrections. And so the first ingredient of the ansatz is that the dependence on the worldsheet variables z and z bar are weight 3 single-valued multi-poly logarithms. Now, this might seem like a very random guess, like where is this coming from? The motivation comes from considering a toy problem, where imagine you just have bosonic string theory. You're starting in flat space, you want to go into ADS kind of perturbatively by like deforming your metric. So that would roughly correspond to inserting a vertex operator like x mu x nu. And so if you take a 4-point function in string theory and then put in this insertion of x mu x nu, and if you evaluate it, up to ignoring some infinities because it's just a toy problem, you will actually see that you get weight 3 single-valued multi-poly logarithms. So this is kind of the motivation for the ansatz. But although, of course, you could just take the ansatz as some like magical guess that these very smart people came up with, which ends up giving the right answer, as you'll see in a moment. The other part of the ansatz is these polynomials that multiply the single-valued multi-poly logarithms. The rule for why they only have a certain degree is that if you then take this answer and expand at low energies, which is when s and t are small, then you expect that certain powers of zeta functions should multiply certain polynomials in s and t. So for instance, like as is well known for the Virasoro-Shapiro amplitude, the r to the 4 correction to supergravity multiplies zeta of 3. And so we expect that to be similarly the case in ADS, and that's why we can't just have an arbitrary polynomial of s and t multiplying these single-valued multi-poly logarithms. Okay, so this is now the second ingredient into the worldsheet bootstrap, which is this ansatz for the correlator expanded into ADS. So now what the worldsheet bootstrap does is that it just demands that these two things be equivalent. So you demand that the block expansion expanded into ADS must be equivalent to your ansatz for the answer in terms of a worldsheet integral. Now, both of these assumptions could have been false, but it turns out that not only are these two assumptions consistent, but in fact, they uniquely fix the answer, at least for the first ADS correction to flat space, which is kind of miraculous. So once you have now fixed this answer, you can now just read off the CFD data as an expansion around flat space, i.e. in this large lambda expansion. And so this program has been done for the first two corrections to flat space, originally in n equals 4 super Yang-Mills, in this paper by Fernando, then it was done for ABGM. And like the check that you're doing something correct is that this matches integrability. For the scaling dimensions, no p coefficients were also matched to some numerical bootstrap results. Furthermore, you can do a low energy expansion and match to some previous results by me and Silviu and others. So this is why we believe this worldsheet bootstrap is correct, because the answers are consistent with integrability. But this was all for ADS higher than 3, which are the more well-known examples. So now let's focus on ADS 3. So we're doing ADS 3 cross S3 cross M4. M4, in principle, can be any of these three manifolds. The ADS-CFT dictionary, in this case, is a bit more complicated than higher dimensions, because there are now two kinds of fluxes. So instead of just having Ramon-Ramon flux, as you would have had in higher dimensions, this term, you also have an SNS flux. And that's something which is special to ADS 3. And so like the sum of both of these guys is what we're going to call lambda, but in principle, there's kind of like two ingredients. So for the pure NSNS case, when the Ramon flux is 0, you're in luck because there's no Ramon-Ramon flux, and so that means we know how to do RNS string theory. And so in particular, in these famous papers by Hiroshi and Juan from, I guess, almost 30 years ago, they showed how you could completely solve everything in principle at finite k from a certain WZW model. But once you turn on Ramon-Ramon flux, the problem becomes as hard as higher dimensions, and you lose the solvability. Okay, so we're going to consider the manifolds T4 and K3. Just because they both have small n equals 4R symmetry. We won't say as much about S3 cross S1, although many of these methods probably apply to every case. Okay, so we just apply the worldsheet bootstrap just as we did in higher dimensions, the exact same method, and indeed it works. This is what I did with DeLeong a year and a half ago. We get the first ADS correction. We use that to read off the scaling dimension of the lowest Reggie trajectory. This is the answer. It's an expansion in lambda, as we saw before. We have a similar result for the OP coefficient. The thing, though, is that unlike higher dimensions, what are we supposed to compare this to? Because there is no integrability. In fact, this is the first result in the literature in the case of ADS3 with Ramon flux, because no one else has been able to compute anything because it's so hard. So in fact, how do I even know that the answer is pure Ramon flux? Because where in my assumptions did I specify it's pure Ramon, mixed, etc.? So in order to just figure out what's going on here, we consider what's called a classical string solution. So for classical string solutions, you take the Polyakov action, which you can define in any manifold you want, at least as an effective theory, and then you consider some solution to the Polyakov action where all the quantum numbers are big, such that you can solve it as a saddle point, which is a perfectly valid thing to do at leading order. So in particular, we let the scaling dimension, the spin, as well as the R symmetry variable j all scale like square root of lambda. And then you can construct various such solutions. There's like many solutions in the literature. It turns out the one we needed was not in the literature, so we had to derive it ourselves. That's the solution which ends up being relevant to this lowest Reggie trajectory. And so if you compute this classical string solution, you get this answer. And so what you see from this answer compared to the previous slide, so the leading term matches, and we were able to compute this for any value of the mixed flux, because it's a classical string solution. So for that, it doesn't care what the flux is. And so we find that this matches our worldsheet bootstrap answer in the case of pure Ramon, which is when Q equals 0. So that's how we know we're doing the pure Ramon case. We also have to fix as j equals to 1, which is basically because it's a certain superdescendant. But the classical string solution, it only knows the answer when all three parameters, delta, spin, and j, are all big. Because everything else would be some kind of like one-loop correction, which is very hard to compute. And so our worldsheet bootstrap answer gave us that one-loop correction. So it tells us that the C of Q is fixed to a certain value. So in particular, we can also compare this classical string solution to the pure and SNS case. There you can compute anything you want from the WZW model. In fact, the answer takes a very simple form. It's like at finite k, this is the answer. You can expand at large lambda, and then it matches the case where Q equals 1, as you would expect. And so this is how we've basically been able to determine that our worldsheet bootstrap answer is corresponding to the pure Ramon answer. And we've been able to get a prediction for this one-loop correction, at least for the case of Q equals 1 and 0. Okay, so next is string field theory in my remaining 5 minutes. So this, I'm basically reviewing a paper by Shi-Yin and collaborators from 2018. So the idea is that you take the WZW model and you deform by a vertex operator corresponding to Ramon flux, which is basically fixed uniquely. So the first correction vanishes. So you consider the second correction. This is equivalent to basically deforming the metric, where Q was the parameter in the previous slides, which was telling you what the mixed flux was. And so the result of their paper is that you can get corrections to scaling dimensions by turning on Ramon flux, which boil down to being a certain 4-point function, where you have 2 of these deformation vertex operators and 2 other vertex operators corresponding to whatever state you're looking at. So it's very general, because this applies in principle to any state you want. And so this is for finite k, but small mu. So why do you need string field theory? Because in principle, everything on the previous slide you could have just fixed with this like regular string theory. Now, the reason why you need string field theory is that this quantity, this 4-point function, is actually not well defined because it's divergent when these 2 operators are near each other. This is basically because conformal perturbation theory is ambiguous, and what we're doing is conformal perturbation theory here. So what string field theory gives you is that it gives you a consistent prescription for getting a finite answer, which in practice just means removing a power law divergence. Anyways, so at the end of the day, you use their method to compute the correction to the lowest Reggie trajectory. Remember, mu is like this small Ramon flux parameter. And then you relate this mu and k to lambda and q in order to compare it to the worldsheet bootstrap prediction. And you find that they are consistent, and we were able to fix this one-loop term for finite q. And so basically, the fact that we're able to use perturbative and Ramon flux to get the answer for finite mixed flux is because the classical solution suggested that this correction term, its dependence on Q, was a finite polynomial. And so that's what we were kind of taking advantage of. And indeed, this is something we observe in classical solutions for many different classical solutions. And so this is how we're able to get like the full answer at any given order in 1 over lambda for finite Q. Okay, so this is another state. I won't go over it in detail because due to limited time, but just to say the method works in general, we can do any state we want. So in conclusion, we have used the worldsheet bootstrap to give the first large ADS radius correction to CFD data of the lowest Regge trajectory in ADS3S3 for a pure Ramon-Ramon flux. This was the first result at strong coupling in the literature for Ramon-Ramon flux in the case of ADS3 cross S3. This is kind of a bottom-up approach because it was based on some kind of conjectured ansatz. And then we have this top-down approach from string field theory, which allows us to get the scaling dimension of any state, not just the lowest Regge trajectory, at large lambda, and for any value of the mixed flux parameter. So it's much more general than the worldsheet bootstrap, although it's also harder. And the way we were able to do this is we basically assume that at every order in 1 over lambda, the dependence on this q, which is like the mixed flux parameter, is a finite polynomial, which was suggested by classical solutions. And then like the magic is that these two things match. Great. Okay, so then these are my future directions, but due to limited time, you can just kind of take a look at them. Basically, just more orders in mu. Also, we'd like to compare it to integrability by computing some other family of states, and maybe look at S3 cross S1.
So before we take questions, I just want to remind you that the next coffee break is short. So I will stand here. Oh, well, now my mic is dead. Okay. So the next coffee break is short. We need to be back here at 4:15. Okay. And so now any questions for Shai? One.
Could you repeat again how you could go from just the, you did an explicit calculation for for mu very small, so very small Ramon flux, and then somehow miraculously you could get it for any value of the flux.
Yeah, okay. So okay.
I didn't understand.
So that was a bit quick, and so I can just go back to the slide. We look at it more slowly. So over here, the first line is mu is like the Ramon-Ramon flux, and this parameter mu is small. It's an expansion in mu, where k is finite. Now we want to re-expand this at large lambda. Lambda is the ADS radius, which is like the sum of the Ramon-Ramon flux and the NS flux. So we're re-expanding in lambda, which is related to k and q as here. And then we're rewriting mu in terms of q. And so in principle, because we only have things that are perturbative in mu, once we re-expand in terms of lambda in q, in principle we only have perturbative in q. And so a priori you only have perturbative in q for every order in 1 over lambda. But then we observed from looking at these classical solutions that at every order in 1 over lambda, the dependence on q truncates. So it could have in principle been a random function of q. It turns out it's a finite polynomial of a very low degree. And so this is somewhat conjectural, but based on looking at those classical solutions, if we conjecture that it is quadratic in q, then this conjecture is consistent with this answer, and then it's also consistent with the worldsheet bootstrap answer. So it's not proven, but there's a non-trivial check from comparison to the pure Ramon-Ramon case.
Yeah, here.
I'm wondering if generalizations of your method, this is for the worldsheet bootstrap case, if generalizations of your method could be applied to theories in ADS5 with less supersymmetry, such as maybe Klebanov-Witten theory or other theories of this form?
Okay, so you could certainly do less supersymmetry. So like one could also consider examples of holography with flavor brains that have n equals 2 supersymmetry. And there you can consider an ADS Veneziano amplitude. And so we did actually have a paper on that a couple of years ago. I mean, you perhaps are considering theories with even less supersymmetry. So I mean, it's possible, yeah. To be honest, I haven't looked into it. I mean, in principle, the method is only really requiring, superconformal symmetry and then some ansatz. And so it could be that it's restrictive enough even for some n equals 1 cases that would be interesting to look at.
I guess I ask because there's obviously no integrability result to compare to, so it'd give new predictions.
Yeah, but even for the 40 n equals 2 case, there also wasn't integrability results in that case. So that was also kind of like a new prediction.
Thanks.
Okay, why don't we thank Shai again, and then we'll be back in 15 minutes.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
尊敬的各位来宾，本次会议即将开始，请您尽快就座，并将手机等通讯设备关闭或置于静音状态。谢谢您的合作。
Ladies and gentlemen, the event will begin shortly. Can we please ask for you to kindly take your seats? We would like to remind you again to switch off all mobile phones and put electronic devices to silent mode. Thank you for your cooperation.
Hello? Okay, it's time. So let's start the talk of the session. The first talk was given by Sridip Pal from HES. So his title is Semi-Universality of the Operator Spectrum of CDFD at Large Spin. Let's start.
Thank you very much for having me here. It has been a wonderful conference. So today I'm going to tell you about what we call semi-universality of the operator spectrum of conformal field theory at large spin. So this talk will be mostly based on this paper that came out in December with my wonderful collaborator Harsh Anand, Nathan Benjamin, Bipul Kumar, Siraj Minawala, Jyotirmoy Mukherjee, and Ashikur Rahman. And I will also contrast this semi-universality with what I call super-universality in two-dimensional conformal field theory. So this 2D part will be based on this other paper, which has been written with Jaishin Chao and Bart van Dries. So let us begin. So let us first fix the convention. So as we all know that CFT has a lot of operators, and we can parameterize these operators by scaling dimension delta and a set of spins j. And today in this talk, another quantity will play an important role, which we call twist. And this twist is defined as delta minus summation over the absolute value of the spins, ji. And as we all know that these are the CFT data, and the CFT data has to satisfy a lot of consistency conditions. So they are not arbitrary random numbers. So the overarching question that today we are going to address is that whether the large spin density of states or this density of operators are fixed or universal by these consistency conditions alone. And a related question which we're going to answer or probe is that how low this twist can go in d greater than 2 dimension. In 2 dimension, this twist is always positive just by unitarity bound, but as we will show that, as we will see that in higher dimension, this story is much more convoluted. Okay. So let us proceed. So there are two routes to probe the large spin sector in conformal field theory. The traditional route is to look at the light cone bootstrap, where basically we look at 4-point correlation function. And there are cross ratios z and z bar. We take z bar to 1 and z to 0. And in this limit, basically we probe all the large spin operators that appear in the phi OP. By doing this analysis, we can basically show that in the large spin limit, essentially the operator spectrum that appears in the phi OP becomes free, and there is a double twist trajectory. And very recently, we have been able to prove and turn some of these results into proper rigorous theorems. But these are all beautiful and very nice. But today, we are going to take a different route to this large spin. And we are going to basically probe the partition function. And we are going to show that this partition function also probes some large spin regime, but this large spin regime is very different from generalized free field theory. In particular, in the context of holography, it can also probe the black hole. Okay. So whenever we think about partition function and we want to say something about density of states, the standard approach is to use the modular invariance. In fact, indeed, for 1 plus 1D CFT, we can put the CFT on a twisted torus, and we can use modular invariance. And we can do some Cardi-like analysis that immediately gives us some large spin density of states. At least at least we can make a statement easily in the grand canonical ensemble, where we turn on beta left and beta right, which amounts to turning on some angular fugacity. But in higher dimension, we do not have modular invariance because we need to put the theory on SD minus 1 times S1. So this tool of modular invariance is gone, so we need to use some different tool to answer some question of universality in this setup. So the honest question is, does any kind of universality survive? And today I'm going to tell you that in some sense there is some universality survives, what we call semi-universality. Okay. So here is the punchline of the talk, that in 2 dimension, as I said, that you have the Cardi-like analysis and you can make some statement in the grand canonical ensemble. And then just by using some rigorous complex analysis, you can show that the large spin density of states is completely fixed by a number, which is the central charge. And not only is determined by a single number, this Cardi density of states, this formula is actually true in all orders in 1 over j, where j is the spin. And I emphasize that this part of the result is a theorem. We proved it starting from some basic assumptions of modular invariance, immutarity, and so on. In higher dimension, as I said, there is no modular invariance. So our result becomes slightly weaker, but still surprisingly, we have a very rigid structure. In particular, we can show for d greater than 2, in the large spin sector, the density of states the spectrum has a universal shape. And here everything, for example, in 2D, everything was controlled by a single number central charge. Here everything is controlled by a theory-dependent function. And here I will, so in this part, I will basically present a physics-motivated argument based on some effective field theory. So this is the main point, that in 2 dimension we have super universality. So this is what I call super universality. And this is because there is a theory dependent function sitting here. This is what I call semi-universality. Okay. So what is the central object of today's story? As I said, the central object is some partition function. So we are considering some thermal partition function on SD minus 1. We turn on some chemical potential for the spins. So here beta is the inverse temperature and omega I is the angular fugacities. And basically there are floor of d over 2 of them, because in a higher dimension you can have multiple cartons. And the idea is to take this omega I and push it towards some extremal value, which is 1. And just like in Cardy formula, you take beta going to 0 limit to probe the large density of states as large delta or large energy. Here the idea would be to study this partition function in the omega going to 1 limit, and from that extract the large spin density of states. And going ahead a little bit, roughly you can think of taking a fluid and rotating it very rapidly on this sphere. So if you turn on only one of the spins, then what happens that most of the physics happens around this equator. And if you go to the co-moving frame, then the co-moving temperature goes high, and this co-moving volume also becomes large. And then we can apply something what we call thermal effective field theory around this equator, and that's where all the semi-universality appears. I will come back to the details later. So what's the main result? So this is the main takeaway message, that as you push these angular fugacities to limit 1, this partition function log of z develops one pole per rotational plane. So you can see there is a product over 1 minus omega I square. So the main point is that this pole structure is completely universal, like this thing appears for any interacting any CFT in d dimension. And then there is a function sitting here, which is a function of temperature, because temperature is fixed. And this residue h of beta is actually theory dependent. So what happens in 2D, this h is completely fixed by a single number, which is related to the central charge. Whereas in d greater than 2, this h is a genuine function, and this function will vary depending on which theory you are working on. And of course, this function is like you can take a beta going to 0 expansion of this function, then you will have a lot of parameters like central charge. Okay. So before moving ahead, let me just take a moment to explain where does this partition function live. So in d equals 2, you can show that the sum that defines this partition function is well defined inside this domain, where absolute value of omega is less than 1. And basically the pole structure I showed you in previous slide, they basically sits on the boundary. But if you go to higher dimension, in particular in d equals 4, you will see that this thing is slightly more complicated, because in d equals 4, the immutarity basically allows you to define this partition function only inside this diamond, where absolute value of omega 1 plus absolute value of omega 2 is less than 1. But as I said, I need to take omega I to 1 to probe the large spin regime. So basically, we are going to go outside this diamond and push towards this corner. And as we will see later, that thermal effective field theory kind of tells us that we are allowed to go beyond this diamond-shaped region. So in this part of the talk, I will take down my guard of rigor, and I will follow the nose and see what the thermal EFT predicts as we push towards this corner. Okay, so this is the plan for the rest of the talk. First, I will go through this higher dimensional idea of applying the thermal effective field theory, and I will show you how this semi-universality appears. Then I will do some checks against rotating black holes and free theory. Then I will explain the same story in 2 dimensions, but now it's the theorem. And I will then briefly say something about the consequence of this kind of semi-universality. Okay. So the main tool we are going to use today is something that known as thermal effective field theory. This has been discussed in the context of fluid gravity correspondence and development around that time by TFR group, Siraj and his collaborators, and also Christian Jensen, Koptun, Meyer, Reeds, and Kaminsky. And in recent times, this has got a new life and reincarnated by a beautiful paper by Caltech group, Nathan, Hiroshi, David Simmons-Duffin, and Jay Hali. The basic idea is that, so even before going to omega going to 1, even before taking the omega going to 1 limit, I am going to explain you the beta going to 0 limit. And later, this thing will connect back to the omega going to 1 limit, as you will see. So the idea is that you are computing the partition function on S1 times SD minus 1. As you take beta going to 0, the S1 becomes very small, and that means you can write down some effective field theory on SD minus 1. Once you write down this effective field theory, basically you have an expansion of the following form, where you see there is the powers of beta. These powers are universal and fixed by the dimension d. And then there are these coefficients ak, which are Wilson coefficients of this EFT. They are theory dependent. As you change the theory, it changes. And there are some functions of omega, which are basically geometry dependent. And if you put the theory on SD minus 1, you can compute these functions explicitly. And also, I would like to mention here that in 2 dimension, only one term survives, which is related to the central charge. But in higher dimension, you have a full series. And this kind of says that why you would expect semi-universality as opposed to some super universal result. So we are going to use this tool later. But first, let me tell you the main answer that we obtained after using this technique. So this is the main result stated in the microcanonical ensemble in d equals 3. So we take large spin limit. We also take twist to infinity, but we make sure this twist over square root j is fixed. And then the claim is that the entropy associated with the operators or density of states in this large spin goes like square root j times some function which depends on the theory. Here the square root j is the universal part, and this function that is a function of tau over square root j is a theory dependent function. The fact that beta was finite in our story is related to the fact that tau over square root j is fixed. And this function s is related by some Legendre transformation related to the residue h of beta that I mentioned earlier. And again, we arrive at this result by doing some EFT kind of argument. So it's a physics argument. I prefer to say it as a conjecture, and we have checked it in multiple examples. Okay. So this is the picture I want you to have in mind. So in the corners, this is a delta J plane. In the corner, you have some bootstrap where you can do numerical bootstrap. Then the usual light cone regime where basically you keep twist finite and goes to spin large. This is the usual generalized free field theory regime. And then on top of that, you have the semi-universal regime where delta minus j goes like square root j, and both j and this quantity goes to infinity. Okay. And you can do a similar thing in d equals 4 also. In d equals 4, there are 2 spins, j1 and j2. And you can show that the spin goes like there is a universal prefactor, which is j1 times j2 raised to the power 1/3. And then there is a little function s, which is a function of scale twist. And again, the scale twist is basically twist over j1 times j2 to the power 1/3. So this cube root is universal, and this is theory dependent. And you can actually do the general D case where you basically turn on all the spins. And you can show that this S divided by this J1 times Jn to the power 1 over n plus 1, this is given by a theory-dependent function. You can play also other games. For example, in any dimension, if you turn on only one of the spins, you can show that the prefactor that will appear is square root j. So you can play all possible games. Okay. So now I will give you a one-slide explanation of how this thing works. So earlier I told you that we have an expansion in the beta going to 0 limit. So this is a high temperature expansion. And this expansion was of the form ak times fk omega times some powers of beta. And this fk omegas only depends on the geometry. So you can easily take this omega going to one limit term by term. And you can show that for each term in this expansion, the leading pole has the same structure. And of course, there is a beta dependence, and the idea is to resum this beta dependence, and then you will get this residue h of beta. And because the pole structure is shared by all the terms, you will have the result that log of z goes like h of beta divided by product of 1 minus omega square. So this pole is a controlled output of the EFT. This is not an assumption. And of course, like this Borel resummation story is the story for another time. I will not go into details. Okay. Moving on. So one might, of course, as I said, we assume the Borel summability. We also assume that, EFT cannot capture the non-perturbative terms. So there could be terms like this in the EFT, and which can come with some coefficient which depends on omega. So we also assume that this kind of terms doesn't appear in the non-interacting theory. And the free scalar field is kind of fine-tuned example where this kind of terms are present, but we have checked that even the presence of these terms are such that our conjecture holds and the log of z behaves like as it should with some proper pole structure with some residue h of beta. As I said, we have multiple checks for our conjecture. So we have done it for free scalar in all dimension. You can also do it for n equals 4 super means in large n limit by doing some holographic computation. You have rotating black holes, gray galaxy, and gas. In all these phases, you can see that log of z has this behavior, h of beta divided by product of 1 minus omega square. And moving on, I would like to flash you the expression for h of beta in d equals 4. This is a beta going to 0 expansion. You can see there are some finite number of terms, then it truncates, and then you have some non-perturbative corrections. These non-perturbative corrections are kind of features of free field theory. Some fine-tuning happens here, that's why this term appears. But the point is that even after this fine-tuning, this result matches with our prediction. You can also do it for as I said, for n equals 4 super means there are 3 phases. Depending on temperature, you can go from one phase to another phase. And in all of these phases, the conjecture holds. And here is the expression for example, this function h of beta in the black hole. Okay. So now I will come back to the boundary case, which is the 2D case, where we can actually do more and prove a rigorous result. So in 2D, the theorem is following, that we consider a unitary CFT with C greater than 1. We assume a twist gap in the spectrum of Virasoro primaries. And the statement is that the smooth spin J density is fixed, not only fixed by central charge, it is actually fixed or universal to all orders in 1 over J. So the leading order result looks like this, twice pi square root C minus 1 J over 6. You can easily recognize this as a Cardy formula. And this leading term has already been reported in previous papers. But I want to emphasize that this result actually holds in, there are some order 1 corrections which you can write down, and then the result is true for all orders in 1 over G. And that's why this is super universal, as opposed to the usual Cardy formula in large delta, where you always have to average over some window, and this averaging process always introduces some order 1 error, which is absent in this large spin limit. So more precisely, here is the statement. So in the numerator, you take density of states at fixed spin, you integrate over some twist interval, omega. And in the denominator, you have the Cardi-like growth. And the statement is this ratio in the j going to infinity limit. This limit, first the statement is this limit exists. Things. Limit exists, there is no limb sup or no limb inf. And not only that, you can introduce a function phi of tau, which is the compactly supported function. And you can ask how this limit is approached. And you can show this limit is approached in non-perturbative way. So the difference between left-hand side and the right-hand side is suppressed by 1 over j to the power n for any n. And from this, you can show that the non-zero smooth density in every such window. So there is a twist accumulation. So every point above c minus 1 over 12 is a twist accumulation point. You can also prove that the maximal gap between the spin j operators goes to 0 as j goes to 0, at least as fast as j to the power minus 1/4 plus epsilon. So these CFTs are really exotic. And the large spin spectrum is really asymptotically dense. You do not need to average over any spin. So for all these features, so you can contrast all these features with the higher dimensional case. In the higher dimensional, we have semi-universality, and because of all these features, I call these things as super-universal. So now in the rest 4 minutes, I want to come back to the general D case, and I want to come back to the question that how low a twist can become. So in D greater than 2, unitarity is weak about how low the twist can go. In fact, there was a paper by Cordova and Dia from 2017 where they showed that basically where they conjectured that twist has to be positive, and NX kind of gives support to this conjecture. So today I'm going to tell you that if you assume some results about this log G, or if you assume these thermal EFT results, then this conjecture actually implies something about the positivity of the twist. So in particular, you can show that the finiteness of log Z and plus unitarity immediately tells you that this twist cannot run off to minus infinity faster than j to the power 2/3. And in fact, you can also show that this thing is sharp, like you can cook up some set of states so that this inequality is saturated. So in some sense, causality forbids the twist from running off too fast. But just staying on the real line, you cannot prove that twist is positive, so you have to do something more. In particular, you can assume, so this is a new plane, nu is 1 minus omega, and you can assume that if you assume that the log Z doesn't have any 0, so Z is bounded in this domain, uniformly bounded, then by using some complex analysis theorem, you can show that indeed delta is greater than equals absolute value of J. And the basic idea of the proof is that on this line, nu equals 1, where omega equals 0, in the beta going to infinity limit, on this line, the vacuum dominates. And then you use the fact that log Z is a nice bounded holomorphic function. You basically extrapolate the limit on this red line to this whole wedge, and from there you can show that this positivity holds. Okay, and this is indeed the strictly, so this infimum tells you this, and this is strictly stronger than unitarity, and it matches with the conjecture by Cordova and Dia. Okay. And finally, you can also do, you can be more creative and you can do more things. For example, in the paper by, in the paper by Hiroshi, David, Nathan, and Jeha, they basically considered some geometry of this sort where you have RD minus 1 times S1, 2 copies of that, and you cut out 2 balls and you glue them together in a proper way. And then you can see that there is an emergent cycle which goes if you follow the red lines, there is an emergent cycle. And then they take this beta going to 0 limit of this cycle to probe the thermal 1-point function of symmetric traceless operator carrying heavy dimension. You can play the same, you can take the same geometry, but now instead of taking the beta going to 0 limit, you can put an imaginary twist along this gluing, and that will probe the large spin limit of thermal 1-point function. And again, you will see that there is a prefactor which goes like j to the power 1/3 times some function which depends on beta, where beta is related to tau over square root j. And you can play the same game with the 3-point coefficient of highly spinning symmetric traceless operator. Okay, moving on, I want to say that there are 3 main takeaways from this talk. The first one is d greater than 2. You have semi-universal result. There is a spectrum has a universal shape, and there is a theory-dependent function that determines the density of states. This is a physics argument we checked in gravity and free theory. In 2 dimension, you have super universal result is determined by one number c to all orders. It's theorem. And there are some consequences of these results, for example, spectral bounds beyond unitarity and averaged OP data, dense large swim spectrum, and so on. And there are some open questions. For example, it would be very nice to have an argument without this high temperature resummation. And in fact, there is a beautiful follow-up paper by Zohar, Feder, and Alessio, where they basically zoom onto this equator region where the physics happens, and they show that there is an emergent PPOF geometry, and by using the large volume limit of this PPOF geometry, they can also arrive at the same result that we obtained. And it would also be nice to have a large N mechanism. So we checked against holography, but there is no honest large N calculation from the field theory side. It would be nice to have something like that. And also, I am personally interested in proving this analyticity hypothesis or understanding better where this zero-free condition comes for the log Z. And there are many more questions that you can ask. And finally, I would like to thank the audience and also thank my collaborators. They have been wonderful, and I would leave with you these 2 pictures, which are the main takeaways from this talk. Thank you.
So, any questions?
Yes.
So you were very careful to point out that in higher than 2 dimensions, you have this physics argument that it's not a theorem.
Yeah.
But do you see what could be the rigorous handles to turn this into a theorem compared to 2 dimensions where, in fact, there are these rigorous handles?
Yeah, I guess one way to be, I think it's hard. One way to go through this Borel summability business, which I am kind of, like, you have to assume that the original expansion is a Borel summable, and then you need to argue that this omega going to 1 limit is a uniform limit. And then, so I know what kind of math conditions you need to impose on this partition function to arrive at a clean result. But then I am missing some physics input which will imply these math conditions, and which of course also includes this zero-free region statement of the log Z. I guess it would be very nice to have some physics input which will tell us about this analyticity property or the zero-free region of log Z. But without modular invariance, it's hard. I mean, yeah. I mean, generally I'm a very rigorous person, but yeah, it's you do what you can do.
Hi, thanks for the nice talk. So for the case of theories in dimension more than 2, are you able to track this semi-universal behavior at infinite distances in the conformal manifold and say what happens to the operator spectrum there, or
I think the statement is true for all CFTs, irrespective of whether you are in a conformal manifold or not.
My question is more if some of the assumptions you use break down at infinite distances.
I think as long as there is a, so okay, there is a, you are assuming, so there is a thermal EFT where you are doing the reduction. And there is an assumption in this reduction that there is no zero modes, like there is a mass gap when. So as long as this assumption is, as long as this assumption holds, everything should be fine. And even with this assumption, sometimes this even if there are zero modes, that just means you have to take care of the zero modes separately. For example, in a free field theory, you do have zero modes. Even then, the conjecture works out. You can check with the plasticity exponential. So I would think that this is pretty generic and universal.
Okay, and you expect the behavior to be the same as you
yeah, that's what my initial guess would be. Yeah.
Any other questions?
Yes.
Thanks for the nice talk. Maybe a detailed question. When you talk about the scalar, free scalar cases, you mentioned you use fine-tuning. What that means?
Sorry, I didn't understand.
Fine-tuning.
Sorry, what is it?
Fine-tuning.
Fine-tuning. Oh, fine-tuning. Oh, yes.
I'm
so sorry. The fine-tuning happens in the following way. So normally The non-perturbative terms goes like e power minus some number divided by 1 minus omega square. So in the omega going to 1 limit, these terms are highly suppressed. But what happens in the free field theory, the charge of the kk modes and the charge under the rotation, they are all goes like n. So there is a cancellation. And because of this cancellation, what happens, this 1 minus omega square goes away, and then you have all these non-perturbative terms. So that's what I was saying as a fine-tuning. But in general theory, when you do this kk reduction, like the massive modes can be anything, there will be interaction, and these terms will all go away.
Okay. With the timing, let's ask a question later. So let's thank the 3D again. Our next speaker is Matthew Dondelson from Harvard. His title will Bouncing of Stringy Singularities.
Okay, well, thanks very much for the invitation and for the introduction. I'm going to talk about this work from last year with Christopher Ayosa and Robin Carlson, and also some work in progress with Henry Lin, Haitian Shi, and Jessica Yi. Henry is at Princeton, Haitian is a student at Harvard, and Jessica is a student at Stanford. Okay, and here we have a string world sheet propagating in a black hole background, and this is the problem we want to address today. So let's start with the motivation. So we can ask, how does local bulk geometry, how is it encoded in boundary correlation functions? And the idea is you go to certain very special kinematic limits, and in those limits, you see the local bulk emerging. And these limits are related to null geodesics in the bulk. So the simplest example is the vacuum 4-point function, which has what's called a bulk point singularity. So here the blue points are on the boundary of ADS, and the red point is in the bulk. And these lines are all null geodesics in the bulk. So this is a natural configuration from the point of view of the bulk, but from the boundary perspective, it doesn't look special at all. So the statement is, in the local bulk limit, this correlation function has a singularity in this kinematic configuration. Because this is not an actual light cone singularity on the boundary, we expect it to be resolved away from large lambda, where stringy corrections are important. And indeed, this is true. So the exponential softness of string scattering converts this singularity into an actual finite height bump. So here we have a string world sheet, and the height of the bump is very large at large lambda. So it's lambda to some power. So that was the vacuum, but now we can start asking questions that probe actual excited states. So for instance, we have a black hole background here. So this is a spatial slice. The shaded region is the interior. The dashed line is the photon sphere. That's the closest you can come to the interior and still escape. And the red line is a null geodesic projected to a spatial slice. So in this configuration, we expect a singularity on the 2-point function at finite temperature. And indeed you find it. So here, omega and gamma are geometric parameters of the photon sphere. Omega is the velocity of null geodesics, and gamma is the instability. So you see that we can really probe features of local bulk geometry and boundary correlation functions. Again, this singularity is resolved by stringy effects. In this case, the effect is the geometry excites modes on the world sheet. So there are tidal forces. And these inelastic effects resolve the singularity. And we might expect that this is more or less general. So maybe a large but finite lambda, these special singularities are actually resolved by string theory. So that it's some kind of stringy geometry. In this talk, I want to ask a more subtle question, and also a more dramatic question. we want to ask about the black hole singularity. So here we have the Penrose diagram of a black hole. The singularity is drawn bent inward. So that's meant to say that, that there's a time delay as the geodesic goes to the other side. And this is a configuration. It doesn't necessarily contribute to the two-point function. So we have to find the subtle way in which it actually contributes. But once we identify that, we can ask, how does the black hole singularity apply to a stringy probe? You might expect that it's smoothed out, but that's what happens when you scatter off orbifolds. Orbifolds look singular in general relativity, but the scattering off of them is perfectly fine. So maybe that's the expectation. The problem is that we don't have control over the bulk here, because stringy corrections are important. It's a strongly coupled worldsheet action. And so instead, we're going to approach the problem from the boundary perspective. This is not going to be easy, because we have to see inside the horizon. So we better have very good analytic control over our correlation functions. But the idea, the hope, is that if we get really good at computing these things, we should actually be able to see signatures of the interior. So that's what I'm going to do today. So I'm going to go through two instructive examples. But first, we have to review how these singularities show up in holography, and in particular, what analytic continuation actually probes the interior. The interior is shielded by a horizon, but the singularity leaves some subtle imprints on boundary correlators. So let's study the boundary two-point function. Here I've put the two operators on opposite sides of the thermal circle, and beta is the inverse temperature. Now in general, this is analytic in a strip in complex time, between minus beta over 2 and plus beta over 2. That's a general statement about quantum mechanics. What about outside the strip? Well, we don't know. And that's where these subtle features are hiding. In holography, at large n and large lambda, to solve this problem, we just have to solve the wave equation in a black hole in ADS. If you go to nice coordinates, you just get a scattering problem. And it's the Schrodinger equation for a particle in a one-dimensional potential. But it's not just any potential. The potential in an ADS black hole is very special. So near the horizon at z equals infinity, it's a sum over exponentials with very specific rates. And near the boundary at z equals 0, it blows up like a power. So these are the class of the potentials you have to consider for a general black hole in ADS CFT. So we have to study scattering theory in this class of potentials, and it turns out it's very highly constrained. In frequency space, you find a meromorphic function, and moreover, it only has poles, no zeros. And for such a function, you can write the function as a product over its poles up to an overall constant c of 0. The poles here are the quasi-normal modes of the ADS black hole. So that's one thing we know. The other thing we know is the asymptotics of c of omega at large real omega, which are controlled by the operator product expansion. And we find exponential decay at large real omega. So if you combine these two properties, you find that the quasi-normal modes come in families of asymptotically evenly spaced lines. So in the middle here, the spectrum can do whatever it likes, but out at infinity, the lines have to be evenly spaced. Here the spacing is r, and the angle is theta. And the temperature, if you compare these two formulas, the inverse temperature is related to theta and r. So now we take these quasi-normal modes, and we plug it into the formula for the two-point function as a product over quasi-normal modes, and then we Fourier transform. And that gives us the answer for C of t. What do you find? Well, we have our strip of analyticity. Here, nothing can happen. And then we have outside that strip. And what you find is a lattice of singularities. So it's spanned by these two vectors, v plus and v minus. And v plus and v minus are related to these parameters theta and r. So note that these dashed lines are, we can call them the real sections. So that's, say, on one side of the Penrose diagram, but translated by imaginary time, beta over 2. And all the singularities lie on the real sections in this case. Now, what's the bulk interpretation? Well, we have a particle that can bounce around the black hole. And it can bounce arbitrarily many times, and as it bounces, it fills out this whole lattice. So each singularity has an interpretation as a bouncing geodesic. Now, the offset in real time corresponds to the real part of this vector v plus. And again, the important thing to note here is that the singularities are in the real sections, n times beta over 2. The reason is because every time the geodesic crosses our horizon, the imaginary part shifts by beta over 4. So this was a specific example, which was the Schwarzschild black hole. In general, you can have more lines of quasi-normal modes, but actually the story in holography is very rigid. So the method we used applies to any ADS black hole, and you always find a lattice of singularities, and they always lie in the real sections. So this is what happens in general relativity. What we want to study today is what happens in string theory. Does this lattice survive? Do the poles move? Do the singularities move off of the real sections? Or maybe they're resolved completely. We don't know. So we want to solve that question. So we need a model where we can actually do this computation. We can't do it in the bulk because we don't know how to solve string theory on a black hole background. So we have to work on the boundary. Now, the ideal situation would be if we could actually do the computation in n equals 4 Yang-Mills theory and just follow the singularities as you start at strong coupling and go down to weak coupling. That's too hard. So we have to take a simpler toy model. And a very nice toy model is the SYK model. So this is a model of a quantum mechanical model of fermions. And the coupling involves a disorder average, so that you have a random coupling with a Q pairwise interaction between these fermions. And at the end, you disorder average over the coupling, and you take n goes to infinity, scaling the coupling in a certain way. So at low temperatures, it's known that the system is maximally chaotic. It's dual to ADS2 gravity. Away from low temperatures, the chaos bound is no longer saturated. High derivative corrections in the bulk are important, so we can call this a stringy black hole. By stringy black hole, I just mean high derivative corrections cannot be neglected. So let's go all the way to infinite temperature, so the opposite regime. In this regime, we only have one-dimensional full parameter, j, and we compute the two-point function of psi in perturbation theory. Now, by dimensional analysis, the only thing that can appear is j times t. And so the perturbative series in J is equivalent to the Taylor expansion in time. Now there's a nice thing that happens in this model, which is that there's a sense in which this model is only slightly stringy at high temperatures. You might have thought this is the opposite regime as low temperatures, so it's very stringy, but that's not the case. And the reason is something we can call the fake chaos bound. So let me explain that now. So it's a conjecture in chaotic systems that these moments, mu2n, which are the Taylor series coefficients in time, grow in a certain way with n. And that asymptotic form depends on this parameter beta naught, which depends on the theory. So this has been checked in all known examples, and it's believed to be true in general. Now, in the presence of this fake temperature beta naught, we call it a fake temperature because in a sense, it behaves like an inverse temperature. We have this stronger version of the chaos bound, which says that the Lyapunov exponent is bounded from above by 2 pi over beta naught. So this is stronger than the usual chaos bound because beta naught is bigger than beta. In this system, you compute both sides, and you find that the left-hand side is 1.24, the right-hand side is 1.246. So the chaos bound is very close to being saturated, and we can hope that there's a sense in which the string scale in the effective bulk is small. And hopefully this is a good model for Yang-Mills theory at large lambda. So how do we compute the two-point function? Well, in large n SYK, the correlator satisfies the Schwinger-Dyson equation. So here you resum these diagrams, which are called the Mellin diagrams, and you have a closed integral equation for the two-point function. This gives a polynomial time algorithm for computing these moments, mu2n, and we ran it up to mu 4000. In the AI area, it's up to mu 50,000. So it can do much better. So once we have these mu's, we can now study the black hole ring down. So in other words, if you compute the two-point function in the time domain, you have exponential decay, and you can ask what are these complex decay rates, which we can call the quasi-normal modes. Now, this is not a black hole, so it doesn't have to have quasi-normal modes, but it turns out that it does. So we find a discrete spectrum of quasi-normal modes, which are the blue points here. And the red points are zeros. Now remember, in holography, there are no zeros. So these zeros are a new stringy effect in the theory, but we see that it looks surprisingly like a black hole. You have these lines of asymptotically evenly spaced poles. It has this nice tree shape, and so in some sense, some of the black hole features survive beyond the maximally chaotic limit. Now, how about the time domain? So we have our power series in complex time, and we extend it beyond its radius of convergence using Padé approximation. So these red points are the branch points that you get by extending to the complex time planes, and the blue points are the poles that form the branch cuts. They accumulate into branch cuts. And in particular, we have our real sections, which are n times beta over 2, beta naught over 2. And the branch points look like they're almost on these real sections. But they've moved slightly off. And by slightly, I mean 0.01, 0.02. So this is what we expected. We expected to find a theory whose string scale is very small. And so the singularities should move slightly off the real sections. And if you plot C of t on the real sections, you'll find bumps of large but finite height instead of singularities. So this is the expected stringy smoothing in this model. Now it's important to note a difference from the bulk point singularity. In the bulk point singularity, the singularity is actually resolved in string theory. It's completely gone from the complex plane. Here, they just shifted a little bit into the complex time plane. So this is important because it says that quantum gravity effects could be important. So in particular, they could resolve the singularity completely. The other thing you can do is increase this parameter q, and what you find is that the tree collapses onto the imaginary axis. So what's the physical interpretation? Well, at large q, we have an effective ADS2 bulk geometry, and ADS2 does not have a black hole singularity. So these bouncing geodesics should disappear, and indeed we find that everything collapses onto the imaginary axis. Okay, so that was our first example, and now let's move to our second example. So far, we've mostly been working near maximal chaos. We started in holography, and then we studied SYK at infinite temperature, which was, in a sense, had a very small string scale. Now we want to ask the opposite question. Imagine that you go all the way to weak coupling, all the way to the opposite regime of holography. Can we see what happens to the black hole singularity? Do these probes disappear, or are they still visible? So we want to now study an example which answers that question. Now, what does large N buy us? Well, in general, large N matrix systems always have a classical description. In holography, this is the classical wave equation on a black hole. And in SYK, this is the G sigma action. In general, it might be hard to identify the correct classical variables. One situation in which the classical description is very simple is matrix quantum mechanics at high temperatures. So this is the BFSS matrix model, which is a model of 9 matrices. P is the momentum, and you have a commutator squared interaction and fermions. At low temperatures, it's known that this is holographic, maximally chaotic, And the dual geometry is the D0 brane geometry. Now, as we raise the temperature, higher derivative corrections are important, and we have a stringy black hole. All the way at high temperatures, you find that quantum effects are controlled by beta cubed times lambda, which is dimensionless. So the system is actually classical at high temperatures. Real-time correlators can be computed using Monte Carlo simulation, but to study complex time, we need actual new techniques. So let's develop that now. Instead of BFSS, I want to study a slightly simpler model, which is the quantum mechanics of a single large N matrix. So we have a quartic interaction and the conjugate momentum P, and we take N goes to infinity. Now, it's known that if you gauge the global SUN symmetry, you find N fermions in a potential, which is known to be integrable. We want a chaotic system, and so let's instead leave the symmetry ungauged, and then we have a chance of chaos. At high temperatures, we need to do classical stat mech. That means that you integrate over initial conditions and time evolve using the equations of motion and multiply by the Boltzmann weight. And this gives the correlation function. We take the same strategy as an SYK. We need to compute many moments and then analytically continue in time. And the reason we can solve this problem in this situation is different. The system dimensionally reduces to standard planar matrix integral. So after integrating out P, the moments take this form. So we just have an integral over x times this exponential with a quartic. And then we have some polynomial in x. So this is the first planar integral that anybody did. And so we know how to do it. Unfortunately, this algorithm is now exponential time. But we can still compute 60 moments. And that's enough to get some physics out. So what you find in the complex time plane are this imaginary singularity and then two complex singularities which are very reliable, say 3 or 4 digits. And in particular, we have a fake temperature singularity here, which is a signature of chaos. Now, what's the physics we have to explain? You see that there's this real-time scale, which is approximately this real-time scale. So there seems to be some emergent real-time oscillation scale. So what's the physical picture? At large n, the path integral is dominated by a smooth eigenvalue density with an edge at x equals a. So it's smooth, and it has no singularities. And the physical picture is suppose that a single eigenvalue escapes this path from the edge at x equals a and propagates in complex time. So let's neglect the interactions of the probe with the bath. Then the classical solutions are elliptic functions, and they have singularities on a lattice in complex time. So those are the singularities of the solutions. The correlator itself has singularities that come from scattering trajectories. So this means that we start at one singularity in complex time, and we go to the other. So for instance, let's start at x1 equals infinity, come in, graze the edge of the spectrum, and go back to infinity. This leads to a singularity in the correlation function. So this is the fake temperature singularity. We can also have a singularity where we propagate in imaginary time, and then we do a half oscillation in real time and propagate to infinity again. And this should remind you of the bouncing geodesic. We're going from x equals plus infinity to x equals minus infinity. In the middle, we're propagating through the thermal bath. So in the end, in this decoupled approximation, you find a lattice of singularities in complex time. So this decoupled approximation exactly explains this real-time oscillation scale because the quartic oscillator has a lattice of singularities. Now, the other thing we have to explain is that these off-axis singularities are shifted upwards. They're not at the same height as the beta naught singularity. So what's the physics behind that? Well, let's recall the D-brane interpretation. We have a probe brane x1, which is escaping to infinity, and it's propagating on the background that's built out of the other n-1 eigenvalues. We have off-diagonal modes in x, and these lead to attractive interactions, which we can think of as open strings. Now, the off-axis singularities spend more time near the bath, and so the open strings yield a longer time delay, and this shifts them upwards. So that's the qualitative story. Quantitatively, you can do perturbation theory to second order, and you can match the prediction from the moment analysis to very high accuracy. And so, to summarize, we've followed the black hole singularity all the way down to weak coupling. And we found the weakly coupled avatar of the singularity, where bouncing geodesics are replaced by scattering trajectories of probe branes. The ADS boundary is replaced by the point where the probe brane hits infinity, and the black hole is replaced by the thermal bath. So to summarize, we've seen that thermal systems at finite coupling behave like black holes, but maybe the geometric features are smoothed out a bit. And you can study these geometric features, but you need to know very high orders in the Feynman diagram expansion. So these are subtle effects, but computable if you work hard enough. One thing we're still missing is a general theory of large N chaos. So the kind of thing I would hope for is like the periodic orbit expansion of classical hyperbolic systems. So this gives you a classification of the discreteness of the resonances, and B, a way to compute them. So we would like to have something like universality in the spectrum of quasi-normal modes, maybe with random matrix theory, or maybe universality of the distribution of singularities in complex time. So I would like a theory that explains that, and I'm optimistic that it's waiting to be discovered. Eventually, we want to generalize to higher dimensions. Can we study what happens to the photon sphere in a microscopic setting in string theory? And there are higher dimensional versions of SYK where you might be able to address this question. We saw this unexplained fact, which is that the SYK correlator has discrete quasi-normal modes. This is reminiscent of an important result from classical chaos, which says that if you have global chaos, meaning every point in the tangent space has exponential growth of tangent vectors, that implies meromorphy of the two-point function in the complex frequency plane. So that's a classical theorem. And what we want is some quantum generalization of this that would apply to SYK. We think the correct language might be operator growth. And so that's work in progress. And finally, what happens to the black hole singularity in quantum gravity? Can we study finite N effects and solve the problem? Thank you.
Okay. Any questions? Okay.
Sure. Is there any corresponding proof in Creel complexity? Because you are studying a two-point function, and the Creel complexity also like study two-point function.
Yeah, I don't know of an application of Krylov complexity to the black hole singularity, but I think it's very relevant for this question of quasi-normal modes. And in particular, you can show that if the Longshow's coefficients are smooth as a function of n, then you can get this meromorphy property. So somehow that's one generalization of a classical hyperbolicity or global chaos to quantum systems.
Thank you.
Hi. I would like to ask why in the classical case there are no zeros, but when we include string effect, that there are zeros in the C omega.
I'm not sure where you are. Can you raise your hand? Oh, okay. Yeah, so it's a statement about black holes in ADS. It's just the scattering problem admits no zeros. So the potential takes a very particular form. And in string theory, you have to do string field theory. that form no longer applies. I think you might be able to get a toy model like this. Imagine you had two fields in ADS, and they were coupled via some kinetic mixing. So that's kind of a toy model for string theory. I think in that model, you'll find that there are zeros of the correlator. So the kinetic mixing in string theory leads to zeros.
I have a question. So here, in the SYK case, you consider only the infinite temperature, right? Yeah. So the analytic strip is not bounded by physical beta, but there is a fictitious beta 0. But in the matrix model, you said there also emergent some fictitious temperature. Or do you have any physical understanding why it emerges?
Yes. The way I think about it classically is, so we have real-time evolution, which tends to do chaotic things like fold trajectories and stretch them. But we also have imaginary time evolution, and that we should think of as rolling down the potential. So in the matrix model case, the fake temperature is just the time it takes for the probe to roll down the potential all the way to infinity. So you can think of it as the escape time.
So okay, I guess you just find the lowest normal mode, quasi-normal modes, and it just identifies the imaginary part as your fictitious temperature.
It's not quite the quasi-normal mode. So the quasi-normal mode is a statement about the frequency plane. But
oh yeah, sorry.
Yeah.
The bouncing
yes.
time.
Yes.
Okay. Okay.
Okay, with time, let's discuss later. Let's ask thanks to speaker of the section again. And also there have the announcement by organizers.
Thank you. Dear participants, please leave the conference room promptly.